you have to say this now or forever hold those values? That means you have it.
Well, I need to learn something new today.
We're all here to learn something new. And on that note, we welcome our next speaker, Alexander Bloom, who will be telling us everything we want to know and more about packets.
Yeah. Yeah, thank you a lot. So usually I work in the OpenBSD network stack and try to make it faster so it uses more CPUs. But I always feel bad about talking about that when I'm at a EuroBSD conference because there are all those FreeBSD guys who are much better in doing multiprocessor things. So I decided to go more to a user level thing. So what can I see and what is the thing that are in the background so that I understand, or that you as a user understand what the packet is doing and how the system reacts to certain things. So first of all, what is networking all about? So that's a very simple view. So we have networks or the internet, and we want to send packets through our system and forward them and connect networks. And the other thing is we run applications in our system where we want to send some packets to. And the kernel has to decide if it has to go up through the stack or if it has to go from one side to the other side by forwarding them. Another view we can have is this layering. So that's not the OSI layers, that are the layers that are actually used. So we have some physical layers, there's the hardware. Then the next thing is the driver. That's where we have some software that directly interacts with the hardware. In the cases I describe here, I basically care about Ethernet. We have some IP stack. In OpenBSD, we wrapped everything out, like x25, it's all gone. So we only do IP. Then we have some protocols on top of IP, that's UDP and TCP and raw IP. You have the socket layer, that's the interface between the application and the protocols. So then we have some tools to measure things and to see things. So I show you things you see, and I will explain later what exactly you see. So you have a lot of counters. So that's netstart minus s. With ss, it only gives you the counters that are not 0. And I only show you a few of them. There are long ranges of counters, and usually people don't know what does all that mean. Then we have PF states. So there are a lot of details in there. You have NUT states, you have non-NUT states, and what does it mean if you have some packets counted in the state? Where is it going? And we have sockets. So with netstat minus AN, you get the sockets. I will go into that a little bit later, where you see that something is going on. So here we have TCP sockets and we have UDP sockets, and you see some queue numbers, and I will explain later what you see there. And you can do TCP dump. So what I did here is a sophisticated TCP dump because I dumped on the ENC interface. So ENC interfaces are for IPsec, and what you see here is the unencrypted packet of IPsec. So so what you see here is an SPI. That's how the packet is linked to the security association. You see the clear text packet here. Then the outer packet, we have tunnel mode. So I have it's an IPv6 outer packet. Then it's an IPv4 inner packet inside, and then you have an IPv4 request. So, and I will show you during this talk at what station of all this processing it is detected that you get all this information out. So next thing is queues. Usually in the IP stack, you have a lot of queues. Maybe not all those queues are the best thing for performance, because queuing things makes things slow. You usually want to process the packet through, but there are some other requirements where you need queues. So usually we have a network interface, that's the hardware, which puts queues in some DMA rings. So the hardware itself puts those packets in those queues. Then we get an interrupt, and the device driver pulls it out. And it puts in an interface input queue. So DLG has created a system where we have those input queues, where we move from the interrupt context. The ideas in the interrupt context should be very short, because it's running, interrupting some things. You just take it out and put it there in the interface queue. And next thing is we have the IP stack. Nowadays it runs in a kernel thread process context, may sleep a little bit there. And currently we run it in parallel on multiple CPUs. That's the things I've working on the previous years. And process those further. And when we want to go to the application, we put it in the socket queue and wait for the userland to take it out. So there's one queue I didn't show you here, and that's more or less a temporary queue where we are in transition of making things more parallel. So when the thing is that when you're working on parallelizing the network stack, you should start where you can put pressure on the system. So we start from the lower part. So we started making the device drivers MP capable and having multiple receive DMA rings. So multiple network cards, modern network cards have multiple rings, and you can put traffic. You can manage them on multiple CPUs, and you put multiple CPUs are putting them in the DMA ring. And then you have multiple interface input queues where the interrupts put them in. So each CPU has one interrupt assigned to it, and they put it in parallel in multiple interface input queues. And so the problem is our TCP stack is not MP ready yet. So we have only one CPU that can process TCP. And we implemented in a way that I've put there where the IP stack is in there, there's another queue. So the lower part is running on multi-CPUs, and I put it in there for protocol processing. And up there, there's only one CPU doing it. So there's another queue, and I want to get rid of that. So that's the goal. So that every protocol is running on multiple CPUs, and I can just forward it. And the socket queue, you must have it because the socket is waiting. The userland has to say, no, other way. The protocol is putting it in, and then the userland is signaled there's something to do, and the userland decides when it wants to take it. So that's why we need this queue. So that's the other direction. Userland puts something in the queue and says, kernel, do something. Basically, we need this queue for TCP retransmits, because when the packet gets lost, the data is still there, and TCP can say, okay, we send it again. We process it in the IP stack. Then we put it in the interface output queue, tell the device driver there's something to do. Device driver will send it and put it in the ring for the hardware. We'll tell the hardware, do something. Hardware will process it. So you cannot get rid of the DMA ring. That's something how the hardware works. The interface output queue, I was asking myself, why do we have it? And I asked DLG and Claudio, and they say that the problem is that telling the hardware do something also takes some time, So writing in the registers. So it's a tricky thing there. We try to accumulate some packets in the interface output queue, and then we tell the hardware, do something. We do it by a special task. So we have a task that says, okay, hardware do something, and when the task is scheduled, then we put it in the hardware. And we see that if we see that that there's also already something running, we sometimes doing without doing much queue, we just go there and say, put it out, do something with the hardware. So now I'm looking at the queues where you can see that the queues are full. Let's start at the socket. So when we use TCP, we use both of the queues. And when you do a netstat and say, print me everything information of the TCP protocols, you do see these receive queue and the send queue. And that's where you can figure out if there's something in there. And if you have some problems with traffic flowing from your user land, you see, oh, something is slow. Is it the kernel or is it the user land? Or if you use relay-D, then it uses both of them. Then you can figure out where the back pressure is, because those queues fill up. And if you see packets here in the receive queue, you see, okay, this user land doesn't take them out fast enough. And so if for example, if this would be relay-D, and you see something here, you say, okay, the bottleneck is further forward in the processing. And so those numbers can get much larger. It's basically the send and receive socket buffer size. And when you see, oh, my packets accumulate in the send queue, then you see, the other side is not taking the packets anymore. And you see, that the bottleneck must be somewhere there. So I use these numbers to figure out why is the TCP getting slow, or who is responsible for not using more of the bandwidth. So we have other queues. That's the queue between the device driver and the input queue. And DLG wrote a quite useful tool, and that's called kstat. With kstat, you can ask the interface driver to provide more information. Don't print everything. There's a lot of output, and just print the one that's relevant for this. So on the output queue, you can see how many packets did I process, how many bytes were in there, and you see these queue drops. So when you see drops there, you see that something is going on, is wrong, that you try to send out more packets than are being processed. So in TCP, this usually doesn't happen because TCP slows down everything. But when you are doing UDP and you see your drops are going up there, you see some problems. So if you see that's Rx is always receive. Rx is the receive queue, and Tx is the transmit queue. So when you see queue drops here, you know somebody is sending me UDP packets or raw IP packets where my system is not fast enough to process them. So the bottleneck is somewhere up there. And on the other hand, when you have the output queue, and we also have some queue drops here, then you know my system is not, my network card is not fast enough to process them. So I didn't run into this problem when I made this slide. You also have a QLAN and a max QLAN, so you can figure out if the queue is busy, if there's packets in there, if you may hit the limit.
Is the queue dropping over timeout or when the queue is full, or both?
When the queue is full, there's no timeout. So the queue is full, and we expect that the network hardware takes the packet. So here the network hardware has to take the packets, and on this side we expect that the TCP stack is scheduled and takes out the packet.
Is there no maximum length for the receive queue?
So the question was, why is there no maximum length of the receive queue? At least the tool doesn't print it. I forgot why it didn't print it. I have to look at the code. But it's a valid question, and I just don't know the answer without reading the code. So, and here we have the DMA ring, which can also get full. So that happens if the device driver, so we only have it at the, for the output queue, and that happens if the device driver has more packets than the hardware can process. So I took an EM interface, that's the gigabit interface, and there it's quite often that happens that you have more packets than you can process. And when you run ifconfig and this queue is full, you see an O-active flag. So the O-active says the hardware cannot process all the packets you put it in, and it sets this flag to say the upper layers to slow down, which means basically drop the packets. So if the device driver cannot put the packets in the DMA ring because the hardware is not processing it fast enough, it says O-active, and the layer above will throw the packets away. So another thing, I already mentioned it, you can have more than one queues. So the EM driver currently only supports one queue, but with IX and IXL and the other 10 gigabit drivers, you have more than one queues. The number of queues depends on the numbers of CPUs in the hardware, and the number of queues the actual chip supports. So even in EX, there are several revisions that do more or less. And so in DMASC, it prints how many queues you have. It's left there, 4 queues, it says. And the KStat queue, the KStat tools, here you can say only show me the transmit queues, shows you the queues separately. So here it shows me 4 queues. On other hardware, it may be 8. And it has an O-active per queue. So here you can figure out, so here it says O-active true, so currently we can't process more packets as the upper layer slow down a bit. And it also counts the O-active, so how many times do I run in this situation? So I took those numbers from, or those examples from my network benchmarking machine. So I quite often run into some problems where I get the full queues and can't process any packets anymore. But if you see, and I also reduce it, so it puts much more data print out there, but I want to just show that that's the relevant part here. So you can see, okay, are my packets full, my queue's full, and if I'm currently stuck and have some O-active flags there. So when you see that, you may have a driver bug, or you see that here we are in the bottleneck. So there was a question. Sorry, a bit louder, please. So the zero, I don't know, I have to see the full output, then I can tell you. So it puts some numbers in there, and EX1 is the interface, and the queue is the queue is 0, 1, 2, 3, and the 0 there, I don't know. I have to look it up.
So if you have multiple transmit queues, the one you would use by default is full, will the stack just travel another queue or still go for packet?
No, the thing is with those, so the question was what happens if I have multiple queues? And the idea is to make traffic distribution. So what we do, so on the receiving side, you have some hashes that are calculated by the hardware, and based on these hashes, that mostly IP addresses and maybe ports, the packets are placed in a specific queue. And the idea is that you want to have traffic that belongs to one connection in one queue on one CPU, because you want to avoid reordering. So if you would process a TCP stream, one TCP stream or multiple CPUs, you don't guarantee that the order is the same when you forward them, for example. And then your TCP performance will drop because somebody in the TCP says, oh, we have reordering, we got something lost, let's reduce the bandwidth. So the idea is to make some hashes on it and place it based on that hash on one queue. And we do it, the hardware does it more or less automatically. And we also have in software some Tirpitz algorithm that calculates some hashes. And based on that, it's put into a specific queue. So when you run only 2 TCP streams and forward them and look at those numbers, you will see that only 1 or 2 queues is used. 1 queue is if you have a hash collision, and 2 queues if it's distributed. But you won't see more than the 2 queues when you have 2 TCP streams. So when you make performance measurements, you can activate multiple, you should use multiple TCP streams to have a distribution and see how the performance works. Okay, now we understand how the queues work, and now let's look in more detail in the IP stack. So here we have the thing where we want to talk to the protocol, to the local applications, and there we go through Ether input, IP input, TCP input, if it's TCP. So it works in the way that we have a lot of function pointers in the kernel, where it looks at the protocol and sees, it's, for example, in Ether input. So the Ether input is found because we know the device driver knows it's an Ethernet device, so it goes through Ethernet input. Ether input looks at the protocol number, says, oh, it's IPv6, let's go to IP input. IP input parses the IP header and says, oh, it's TCP, let's go to TCP input. And TCP knows, oh, I'm TCP, I have a socket, and let's put it in this socket by using port numbers, basically. And the other way also works that way. We have a socket, we know it's a TCP socket, put it in the socket buffer, with TCP output, and it processes, so basically TCP output sees a lot of data in the socket buffer and makes a packet the size that fits into the Ethernet frame. So there's some layer violation. So TCP assumes that the Ethernet and the IP header will take some space and knows about the MTU, and that's the way it reserves something and figures out how big it should be, and also takes some path MTU discovery into account. And IP output, again, the route lookup has been made before. So basically, TCP output does a route lookup to know which interface it's going out, and the path MTU is also at the route information. So the MTU, the path MTU, so it knows how big it should be, and IP output just adds some header on it, and also knows in which interface it will go. Gives it to Ether output, which adds the Ethernet header, and then we put it in the device driver queue. And what happened when we want to forward? So forwarding is on the IP layer. IP input does the route lookup to figure out, is it a local address or is it a remote address? And if it's a remote address, it just puts it to IP forward, which will put it in IP output. So in IPv6 logs, it works similar. Shouldn't be IPv6 here? UDP is here. Okay. UDP. So as I mentioned before, the UDP does the other way around. The send buffer for TCP is done for retransmits. So TCP always needs a copy until it's acknowledged by the other side, then it throws it away. As we don't get acknowledgements and have no retransmit in UDP, we we don't put it in the send buffer queue. So there are some small differences depending on the protocol. Now we have IPv6. IPv6 is usually a bit odd. You see it here, the IPv6 forward goes directly to Ether output for whatever reasons, but that means all the code in IP output that deals with putting it out has to be copied to IP forward. So when you change something in IP output and want to make the similar change to IPv6, you also have to touch IP output and IPv6 forward, because the code is duplicated. Yeah, that's a karma decision. I think FreeBSD also has it that way. So now you've learned how the packets flow in, and now you can see, or now you can understand more of the NetStat output. So if you see something in IP, you know, that's the IP input and the IP output numbers that increase. Similar for TCP and UDP. So those counters of the packets are done in the IP input, IP output, UDP output functions, and you know that those functions are responsible for increasing those counters. Now we come to PF. So PF is basically called in IP input and in IP output. And it gives the PF test function, which does all the PF processing, the direction. So when you write a rule, you write PF in something, and you have PF out rules. The PF in rules are matched on the left side. The PF out rules are matched on the right side. And the packets always go through IP input and are tested, and then the decision is made, is it TCP input or is it local protocol input, or is it forwarding? And now you have the picture for IPv6. As usual, IPv6 is a bit odd. And as explained before, it works more or less the same, except that the code that calls PF test is copied in IPv6 forward, and it's called there. There's also a forward thing, which does basically the same as the output direction. So you don't have forward rules, you have output rules. But the forward case, it's used to do fragment refragmentation. So what I implemented for IPv6, it was already there for v4, is to packet reassembly. But then you have a mandatory path-MTU discovery for IPv6, also for UDP packets. That means that you have to refragment it in the same size that it was before when you forward it. And the PF detects, oh, I'm in the IPv6 forward path. It's only there when the forward direction is given, and there it says, oh, it has been fragmented before and they're reassembled before you make the test with PF. And now we have to refragment it to the same size as it was before. And that's basically what the forward direction is used for. So now with this understanding that we have PF going in and out, you know why we need those rules with in and out, because the in rules are matched on the right side and the out rules, in rules on the left, out on the right, with the previous picture. And so what we see here that are the default rules. The default rules, when you have a default PF configuration, you load in that. You can also match on users, and those user matching only works on the right side when you go out from the stack. Otherwise, there's no user information. And those interfaces where you match in on something, that only works on the left side, because there it comes through an interface. Okay, now when it comes to states, the states are seen as both sides. I'll just go back. So you have a test in and a test out. And you have a packet direction and you have a state direction. And for example, if the state is created when it comes in, so we create it here, and when we send the matching packet out, we send it with out direction, but the state was created in, so it has to match the different direction than the state. So there's some changing direction in the code. So if you have an in state and an out packet, then it has to be reply packet. And there so Henning says yes. So it's a bit hard to understand. So you have states that have a direction, and you have packets that are in a different direction or in the same direction, but when they are in the different direction than the state, then the matching criteria for in and out IP addresses and ports are switched.
Well, it's quite obvious. You create a state on the inbound packet.
Mm-hmm.
The reply packets obviously have the destination address, which is the source address to the state, because it's the reply in the other direction.
Mm-hmm. Exactly.
In theory, it's simple. In practice, it is easy to get lost. I'm on your side there.
Yeah. You look at those switch, and you still think where does it match to. But you have this, to keep this in mind, the state is shared between both. The PF test knows the direction of the state, knows the direction of the packet, and knows when to switch source and destination. So we have some pseudo devices. Question is, what's a pseudo device? So we know what hardware devices are and what not. And we look in the man page and see, if we do ifconfig minus capital C, we can see all the pseudo devices. And basically, pseudo devices are network devices that can create it on the fly. And I want to go into VLAN because it's quite simple. And all those devices work a little bit different, and you can talk about each of them for a while, but I don't have enough time. So I just talk about VLAN. So you create them with a create command, and depending on the device, you'd have to say some other things. Here, for VLANs, you get the VLAN ID and the parent interface. So let's look, how does it work without a pseudo device? So if the network interface, the hardware, it puts in the DMA ring, and that's a receive ring, then it gets an interrupt, then you have this if queue thing, and there you put it in the interface queue to process it further in the stack. And the if queue input has the TCP dump thing. So that's Berkeley packet filter. So when you call this function, the userland will see it in the TCP dump. So here the if input queue input shows you the packet in the TCP dump. And you change context. So between those two queues, you are so at the bottom you're in the hardware context, then you are in the interrupt context, and up there you are in the softnet kernel thread context. So, and when you take a VLAN, you also change some pointers where the packet, where the function is, some function pointer, which function to call to continue processing. And there you, for VLAN packets, you just go between the ether input after the interface input queue, and you call VLAN input, which strips off the VLAN header. Then it calls some other function, and here the EF VLAN input it's called. And here we call again MPF, the BPF thing. So you see it again, the TCP dump. So you have the original TCP dump output here from down in the IFQ input. You see it once, and you strip the VLAN header, and then you see it again. So if something is wrong with your VLAN, and you do TCP dump on the VLAN interface up there and the Ethernet interface down there, you see, here the packet is lost. So that's the other direction. packet comes from the stack or from forwarding. You put it in the interface queue, call if queue start to tell the hardware driver to do something. EM start dumps the packet just when it puts it in the transmit queue. So you don't know if the hardware if the packet goes out if you see it in TCP dump, but you know the driver did all it could to put it in the hardware. So if it doesn't work now, if it doesn't show up in the cable, you have a driver bug, hardware bug, some incompatibility, but it's quite down there. So all the IP thingy has been done. And also here we move some pointers around and just go a little bit different path when you have the VLAN in between. So you enqueue it to the VLAN, not to the real hardware. Then VLAN transmit prints it without the VLAN header. Then it injects the VLAN header. VLAN inject will put the header in there. Then you put it to the interface, and then you see it again in TCP dump just before the hardware has to take over. Yeah.
Just point. So if you do TCP dump on the inbound and you miss a packet, then it is not PF blocking it because PF comes in 2 layers later. But you're just really not receiving it. On the other way around, on the output interface, you see the packet just before it enters the cable, more or less, so it is post-PF processing. It can be tricky here and there, especially with encapsulated stuff.
It's true as long as you're not looking at pseudo devices like VLAN, because then the thing happens again. But yeah, the rule of thumb is TCP dump is outside PF. It comes before on the inbound and after outbound. Yes.
Yeah, that's the idea to show it the big picture. Where's PF? Where's TCP dump? Where are my queues? Where is it full? Where gets the packet lost? And you have to know this picture to understand the measurements that you see. So we have 6 minutes left for IPsec. So first thing you have to understand, you have flows and you have SAs. So SA is the security association. So flow basically says, is about the unencrypted packet. So it does a match on the inbound network and the outbound network. So that's from and to. And you have a flow for incoming packets and you have a flow for outgoing packets. It matches on from and to. It's a radix tree. It puts both addresses with both net masks into this radix tree. So it is a non-continuous net mask because it has 2 addresses in there and makes the best match. And then it sees, oh, when it matches the from and to, then I have a local and a peer. And this local and peer must have a security association. And there you have the key. The key is at the SA. And ICD puts those SAs in, and you can. There are 2 modes where you can say, oh, the flow should come from the ICD, or you should configure it statically. It's not that easy. And here I showed the tunnel mode. You also have transport mode. So there are a lot of options what you can do wrong. And so at the end, you have an SPI and a key. So the SPI is for the encrypted packet. The encrypted packet is always matched against the SPI. And the cleared packet that we want to process with IPsec is matched with the flow. And you have in and out. So both directions are more or less independent of each other. So how does it work? So we are in IP input. IP input does the route lookup. The route lookup says, okay, either it's to be forwarded or it's local. If it's local, it goes to IP deliver. There we process the headers. So if it's maybe clear text, then just go to TCP input. Or we say, oh dear, now we have an IPsec packet because it's an ESP packet. Then we go through IPsec common input, and it calls get TDB the tunnel descriptor block. Yeah. I looked it up before and now forgot. So, and here we put in the SPI. The SPI finds the flow. Then we go to ESP input that calls crypto invoke, and this decrypts the packet. Then we go to the common IPsec common input callback, and there we go again to the TCP dump, the BPF. We have a direction incoming, and we use this pseudo ENC interface. So here you see that what I showed at the very beginning, the clear text packet with all the headers and all the information. So and then we go back to the deliver loop. It's a for loop processing the headers, but now it's unencrypted. And here we decide again, do we want to, is it IP in input, IP in IP? So if it's IP in IP, we are in the tunnel mode. Then we go to IP input and can forward it. Or we say, oh, we are in transport mode, then there's directly the TCP header, and we just go to TCP input. So we can also do it the other way around. Here we come from IP output, that could be local stack, or we come from IP forward. IP forward also calls IP output. And in IPv6 it's different, but I don't have a slide for that. So IP output does it does an IP output IPsec lookup. There it looks in the flow. So does the packet match the flow? If it doesn't, yeah, we just go to the ether output, done. If it matches, we get the TDB by destination. So we put the source and the destination address in there, and that's basically the flow information, and then we get the TDB. We go to IP output IPsec send. That calls ESP output, which puts it through the TCP dump. So here we see the packet in clear text. Now it's going to IPsec with all some IPsec information attached. We call crypto invoke, which encrypts it. We go to IP process done, which goes back to IP output. And there we just go to ether output with a new encrypted packet. So you see here we go to IP output twice. So we also go to PF twice. You can do PF on the encrypted packet, and you do it on the unencrypted packet. And the difference is the interface. So you see we have those pseudo interface ENC0, and the unencrypted packet will go through ENC0 with ENC0 through PF, and the encrypted packet will go with the interface that will come that comes from the route lookup. And by the way, I just forgot to mention it. Here it's the same. The IP input is also called twice. When we first go in, and then blah, in tunnel mode, we go the second time in, and there we also call 2 times PF test. So I have 2 minutes left. So some tricks. So what I usually do when I try to debug a network problem, I take all the counters, I do something, I take the counters again, and I throw it in diff. The only thing here you see, okay, something happened here in TCP, blah, blah, blah. The only thing you have to do in your head is to subtract those numbers. I wanted to write a tool and put it on the slides, but I've not finished it yet. So for some of my measurement machines, I have some Perl code that does the subtraction automatically, and I try to put it in a separate tool. So the other thing is, I've seen one of those netstart counters. What does it mean? So if you see netstart minus SS, I have 81 packets not forwardable. Then you grab the not forwardable in the netstart source code. Then you find this line. Be careful not to grab too much of it, because then the netstart puts an S there if it's plural and no S if it's singular. So you only grab a not forwardable. If you grab on packets, then it won't work. Then you find this. Oh, there's a slash too much. So it's IPS can't forward. That's the counter in the kernel. So you take this and grab in the kernel. And then you find multiple places where it is, and there you can see the condition why this counter goes up. You can do this with every counter, and then you find, here something is wrong, and you look at the if, and know, and may understand what happened there. So that's a tip for developers. Always check on error. We always do that, oh? Very good. So if something goes wrong, count it. And please use a unique counter. So in the example before, I had 4 places where this counter goes up, and then when you debug your network, you're saying, oh, what did go wrong? Was it here or there? Or, But if you have a unique counter, it takes a little bit more effort to put it in init.c in netstat, but then the users will see where it happened. Okay, some final words. So when I did those 41 slides, I looked in my abstract and figured out, oh dear, there's more described in the abstract than I can talk about in 45 minutes. So I didn't only a little bit say about routing. I completely missed ARP and neighbor discovery. So bridge and web, I looked in the code, and oh dear, it's complicated. And hardware offloading, yes, I know how it works, but it would take much more time to explain how it works. So we have checksum offloading, and we have TCP segment offloading. So, but I will be here next year, and I can say this. So here are the slides. I put them on GitHub. And the first question is, do we have time for questions?
I'm afraid you stand between these nice people and their lunch.
Just go back one.
So I would like to thank our speaker, and I will throw him under the bus.
Thanks a lot.
And say that if you can find him during lunch, I'm sure he'll be delighted to answer any questions you have. Thank you very much.
Thank you.
That was very information dense.
Topler's talking about building SD-WAN sometimes. We won't have any PA in here, so we believe you can hear what Jason says. But if there are any questions, I will come with the microphone. Just raise your hands and that's it.
Thank you. Like Swiss clockwork, it's just straight into it. 3 o'clock on the dial. Thank you very much. I hope everybody's having a great conference. It's been an excellent conference for me. Catching up with old friends, meeting new friends. I've had a great time. I have been stuck between Brooke Davies and Kirk McCusick, so it's an honour to have you all here because the two heavyweights is quite a hard act to beat. So this talk is about building an SD-WAN appliance suitable for the Australian health sector, NFP, NGO. So I've also given a similar presentation internally to my peers in Victoria, and everybody seems to have a consensus that what we've done is pretty well on the money. So my name's Jason Tubner. I'm the ICT manager. When I worked with the team to actually build this device out, I was actually the ICT senior security lead. So yeah, I've had sort of a promotion for the last 12 months, though it's still only an acting position. So the introduction of this talk is, we'll just touch a bit about me, and then the organisation I work for, which is La Trobe Community Health Service. I'll go into a history of our SD-WAN journey. This is not the first incarnation of this device. We had a previous version, and we took a lot of things that we did in the previous version and reiterated on that because there was a lot of deficiencies that we found, a lot of complexities that just wasn't good for us to be able to run a professional organisation. We'll cover some design choices that we had to take into consideration as we flesh this out. We will touch on OpenBSD VPN and routing technologies. Everybody knows OpenBSD has got an awesome stack, top to bottom, for routing and VPN. Unfortunately, the stack is not performant if you're trying to move 10 plus gigabits per second through it, but it's getting there. The team are working on it. It's great to see, but for our use case in this appliance, we only need to be able to hit 250 meg, so it's fine. And then we'll touch on Ansible orchestration that we've used apart from auto install of OpenBSD. We'll also talk about the orchestration using Ansible and how we hand off a device after auto install and then progress it into the fleet. So about me, I have 31 years of IT experience. I didn't go to university. I was straight out of school into a PC support role, and then I cut my teeth on some VMS and some Alpha stuff, and then that led me through to Sun and Linux. The Sun stuff was really good. I enjoyed doing Sun stuff. I was a Sun consultant in the late 90s in the dot-com era, and I also did some consulting gigs overseas, so it was actually a fun time until it all blew up. But during that gig, I did have one of the colleagues, when I was trying to get XFS working for Linux up and running, the colleague came over with an OpenBSD set and said, try this. And I did, and the man pages were absolutely top-notch, and ever since that, I've been a BSD user through and through. I'm a user and advocate for OpenBSD and FreeBSD, and as you can tell, you may have heard my voice from previous episodes of BSD Now. So I'm a co-host with Benedict and Tom, and Tom's Dragonfly Adventures. I do have a life outside of computers, and that life is ultra endurance bikepacking. So the picture here you see on the screen is me in front of the Sydney Opera House, about to embark on a 2,500k journey across the continent. We do crazy stuff in Australia, even though there's dangerous spiders and snakes and that sort of stuff. It's pretty rare that you get hit by one of those things. So, I like my ultra bikepacking because it takes me away from computers. My phone doesn't work, I can't get contacted, and you just break everything down to simplicity. And it's just a nice feeling to have. A bit about La Trobe Community Health Service. We are originally a Gippsland base, so in Victoria it's got regions, and Gippsland is a small region down to the east of the state, and it's quite a sizable amount. However, we did acquire some contracts from the federal government to offer NDIS services. So NDIS is the National Disability Support Scheme, and we have staff that are in geographical regions that allow clients that have mobility issues and other sorts of issues easy access to the services that we provide. We also provide dental and doctor services, home care packages, so people can stay in their home longer and not have to go to a retirement home. So we have a huge portfolio of services that we offer. We have 1,500 users on staff, so that means that ICT, we have basically 30 ICT staff. People think that that's crazy, but when you have all that knowledge in-house, you can solve a problem. The problem with outsourcing is that you lose that knowledge and the consistency and currency of the services or the systems that you have on your watch. So we have 40 sites across Australia and 3 across Victoria and 3 offices in Sydney. We cover a landmass of 230,000 square kilometres, which, you know, in rough size is Romania or Laos or Minnesota. So that gives you a sort of an idea of how big. And we don't have all of Victoria, so just even Victoria is larger than that size. And our motto is better health, better lifestyles and stronger community. The idea is to keep people within the community and live a healthy lifestyle. So we had a SD-WAN journey that we've previously been on. So in 2017 at BSDCon, I actually talked about this particular design that we had. I was doing half of the rollout before getting on the plane to go to BSDCon. But we did come up with a cost-effective hub and spoke solution. So we didn't want to go complex where you have interconnecting sites and things like that. A hub and spoke just made it easy for the network guys to actually determine, you know, where faults were inside the environment. We used OpenBSD with Beehive host, so there was a reason why that was. At the time, we had to have print servers that existed out in the field on each site, so we needed to have a way of being able to have a router and a Windows server sitting on each site to do what we needed to do. We rolled it out initially with 11.1, and then we've upgraded in place up to 14.0 until we were at the point where we were migrating to the new solution that we're talking about today. We used Super Micro servers, which is the 5019A-FTN4. That's an Atom-based server that we used. The reason why we chose that initially was that it could handle a hostile environment. It was a Atom-based CPU, didn't generate much heat. It could go into a broom closet with lots of dust and chemicals and that sort of stuff, and it was fine. So, but the downside of that was it was extremely slow. Even though I could run Beehive, it was extremely slow. So we upgraded to the 5019SML, which had an E3 Xeon CPU, which solved the problem and made it fast. I didn't get complaints from team members and things like that. We layered up the OpenBSD router with technologies such as PF, OpenID, RIPD, and VXLAN. Now, people are probably saying, why did you use RIPD? And that's what we had from an ISP perspective at that time. We didn't have an option to use OSPF or BGP at the time. We do now. That problem's been solved. But our network was running with RIP for close to 7 years. And we didn't really have an issue. There were times it would flap and things like that. But, you know, overall, RIP served us well. Peter Hessler laid the challenge down. He goes, you'll never get it converted over to OSPF or BGP. And I said to him, I said, challenge accepted. And yes, we did get it there. And yes, it was successful. And no, we didn't have an outage during the whole part. We were able to slowly roll things in and out, and we never had an issue. So basically that's saying, you know, the BSDs are exceptional at being able to be configured and not be overly complex to be able to work out what you're actually doing. We used DH Client and DHC Relay. DH Client was the original before DHC Pleased. DHC Pleased is far better than DH Client. I'll go into some of the issues that we had with DH Client and also some issues that we had with DHC Relay. We used UDP syslog, which took our logging of PF and exported it to syslog-ng that was on a central server that then goes to our SIEM SOC. And we grew to 25 sites using this topology. So it was one that we were rolling out probably for 5 sites, and then it ended up being 25 sites in the end. So certain design choices when we did this were no longer applicable. We couldn't continue down this path of manually having to configure and upgrade and do all that sort of stuff on this. So, the history of our SD-WAN journey. We used a hub to concentrate all the spokes into, so roughly 11 machines. They're a bit, it depends on the balance. They will fluctuate from time to time depending on when we bring new sites online or take sites offline. And they go into a single connection. These 2 hubs were nested within a FreeBSD Beehive hypervisor. I can tell you without a doubt that that thing is so reliable. We had problems when we had the hubs in VMware at the time, and VMware would come in the morning and there would be a debug prompt, and it's like, oh great, we've got 10 sites down. And it's obviously just something how memory management with inside VMware worked, but we never had that with Beehive. We had 2 hubs and the main firewall running in one 2RU SR650 from Lenovo. So that's how solid and reliable it was. The pros that we had, it was extremely stable and efficient. I talked about that a bit earlier, but it was something that the business, my manager, went to their manager and said, hey, we're doing this and saving this much money. And what that means for a not-for-profit organisation means that the funding that we get to deliver the services for our clients can go to delivering that service for the clients. So I thank all the BSD community for the tireless volunteer efforts that you do, because that does help people indirectly down the chain where the funding goes to the correct place. It was extremely low cost. The only thing that we had to buy was the servers. We got a reasonable price at the start, but then they started going up. So yeah, we weren't really happy with Supermicro. I'm going to touch on that about my beefs with Supermicro shortly. It scaled exceptionally well. While I talk about the configuration and trying to manage that over 25 devices, it's still, when I say scaled, I mean that the device could scale infinitely, basically. And if we needed something, we just spin up a 3rd hub. So it wasn't a problem with being able to deliver internal services. And we push, Patch Tuesday goes out to 1,500 odd devices. And we see on our IX, our Internet Exchange, it just rockets up. And the hub's just pushing stuff out our edge to the ISPs. And it's awesome. It's just like, that's with OpenBSD. We're moving, 3 gig per hub without an issue. So while there is performance constraints above 10 gigs, under that, it's fine. The network traffic path was easy to determine faults. So we had, being hub and spoke, it meant there wasn't that much because you're not doing interconnects between different sites. So using a basic routing protocol like we did with RIP, we could see where the particular issues were. There was issues for UDP traffic, I'll get into that, but yeah, that was basically the only thing that we had an issue with. So when you see NBN TC4 connections, that is a basic connection that we get from our national broadband network, and it's just a 140 or 250, 100 connection that is quite cheap, and we get a 4-hour SLA on that, and it's cheaper than buying the equivalent WAN service that we would get from the ISPs. While the WAN service might be symmetrical, we find that if we've got a high bandwidth site, 250, 100 is far enough bandwidth that the site will never grind to a halt. There is one thing that we were able to offload internet access at those sites. So instead of going through the main firewall, they go through the firewall on the site and straight out. So you basically got split networking. And we had the ability to secure traffic and control data quality. So we used QoS to manage the egress traffic, so we didn't hit limits, because what happens with NBN TC4 connections is they've got heavy polices, and they don't just throttle back, they just drop packets. And then you can imagine what that does to voice calls. So using QoS features that are within OpenBSD and IKV2, we could layer the wire with a secure connection, and that way the ISP couldn't actually interfere with any of the traffic. We did have issues with some of our corporate WAN networks where the ISP could see what was happening on there, and would put QoS and do all sorts of traffic manipulation, and we'd get like you can't hear anything on the end of the phone. What this did was allowed us to bypass all that. The cons. So issues with Supermicro support. In Australia, Supermicro don't exist. It's fine in the US. I'm not sure about Europe, but all our stuff had to go to Taiwan, which was problematic. Is when it goes to Taiwan, we've got to pay duty back into Australia again. So it's just like, it always cost us money to actually get these things done. So it was not a good decision going down that path. But really, for short depth servers, they're the only one on the market. Like you look at Lenovo, they don't have anything like that. So that's why we went with Supermicro, but we went with commodity hardware moving forwards. So managing the fleet was overwhelming. I touched on that earlier. The problem with when we had 5, it was fine. But now we have 25. You had hypervisor maintenance. You had 2 upgrades of OpenBSD during each yearly cycle. And PF rule maintenance. That was a nightmare. When you had block lists and you had to go and put block lists across multiple different servers, it was A, inconsistent, B, you didn't know where you're up to, and C, it was just something that nobody ever wanted to do in the business. So yeah, that was one of the cons. We found IKV2 configuration wasn't resilient enough. The reason for that is we had VXLAN issues where it would fall off IKV2 because you're overlaying the ENC0 device. So it wasn't an ideal world. It worked and it was resilient, but it wasn't resilient enough. And then we'd get route table corruption causing havoc on UDP services. So this is where I have beefs. And when UDP services start up in OpenBSD, they look at the routing table and track the routing table. Now, if something happens to that routing table disappears, it will actually use the default route after that point, even if the routing table reappears, because it's done privstep and it doesn't read the routing table anymore after that. TCP traffic does not have that issue. However, DHC relay and syslog were having that issue. So we did fix that particular issue using multiple different methods, and we'll touch on that. So the evolution of design considerations. So we wanted to move to a more robust configuration using LO1. So using a loopback interface for IKV2 allows you to do NAT translation on that. So you use an internal IP address, and then you do a NAT translation out the firewall to do that. What that does allows you to use any and change any particular network connection. So you can go from your TC4 connection to a 5G modem when there's been a network outage. It's using NAT translation, so it doesn't matter. IKV2 internally can track that using source IDs, and that solved our problem there. We wanted to reduce the pseudo VXLAN interface complexity. Problem with VXLAN is that it's great. It's a brilliant protocol, but it was overkill for what we were using it. We moved to DHC pleased. That's a godsend, because we used to have to write some hackery scripts and things like that to actually, when you couldn't ping quad 9 anymore, reload DHC client, DH client, yeah. So DHC please fixed all that. You can basically, when you get a link state change, when the ISP is doing maintenance or whatever, it just gets another IP address and away it goes again. We need to be able to do a DHCP on our ISP. That's the only way that it does authentication to give give a static IP address back to us. We reassessed the use of DHC relay, being that it's UDP and we can't do anything with it. We went, okay, well, let's go down the chain and work out what we can do. Can we do it in the switches? And then change out UDP processes to TCP where possible. So we've got syslog running on TCP now. No problems at all. Routing table can disappear, come back or whatever, and it's no particular issue. And the other design consideration was the networking stack. I told Peter Hessler gave me the challenge. So challenge was accepted and we achieved it. Additional considerations was we needed to use commodity hardware. As I explained, Supermicro was causing us particular issues and we didn't want to go down that path. We want to just have a stack of machines sitting on a shelf that we can just like take them out, do the auto install, take it outside, drop it there, push all the Ansible scripts and it's up and running again. And it's at the point of where it was. So you're not trying to restore, you making an ephemeral device means you're not trying to restore something. You are just using, the configuration that was last pushed to that machine again on a new machine. So the machine had to be disposable. We wanted serial ports, obviously. I like to go out, if there's particular issues, I'll go out to a site to actually plug a serial port in. And it had to have a quad port Ethernet card. So as long as it had a PCIe 16, and I think you can even use a PCIe by 4 to do that. But yeah, as long as it had PCI, which they do because you've got to be able to put a graphics card into it. Automation. We needed to make sure that the builds, upgrades and maintenance were automatically done. I didn't want team members having to log in the machines and try and do upgrades or tinker with configurations, and sometimes I come past and they're in there and I give them a little tap on the shoulder and say no, no, no. The idea is that they can sit back and just use Ansible to do everything that they need to do. So I didn't want them logging into devices, and we wanted to have as zero-touch install as possible. So while we have to press A, I mean, you can make the build environment be completely zero-touch, but the guys just put it in the build lab, put a USB stick in it, press A, and away they go. Terminating spokes into OpenBSD hubs on VMware vSAN. So we do have a vSAN cluster, so it's not to say that a Beehive has been unreliable. It's just really taking more hardware and reducing our power footprint inside our data center. Enter Sec4. So this is a great story, and it was written by David Gwynn from OpenBSD at the University of Queensland. He acknowledges and credits that in the code. So if you go and dig into the code, he actually acknowledges that his employer paid for this. It was to solve a particular problem that they were having, and we had as well. But David and myself were on the same timeline, so we get to have good conversations about stuff. And it also helps when I hit an issue and I can send him, can you fix this? And then we work through it and solve the particular problem. One of those particular issues was where there was a loop inside the SEC interface when BGP would drop, and then all of a sudden it would just like start feeding into itself, and the machine would feel like it just locked up. But that was just because he just had a slight code error, but using it in production sort of fleshes these sorts of things out. So the SEC interface is a pseudo interface added to OpenBSD, and the quote from the man page is, "The SEC driver provides point-to-point tonal interfaces for IPv4 and IPv6, protected by the IPsec encapsulating secure payload ESP protocol." The IPv6 version using OnSec, I'd use that for my home lab between 2 points, and it uses link local and it works absolutely perfect as well. So there was a BGP issue across link local, but again, the OpenBSD developers, especially the ones around BGP, fix that particular issue as well. So please use IPv6. It's like people don't realize that North America and Europe have probably got plenty of IP addresses, but Asia does not. And if you want eyeballs, you want 2 billion eyeballs, IPv6 is where it's at. So just keep that in mind when you're building networks. Tightly integrated into OpenID. So it's another line parameter inside OpenID. So in FreeBSD ports, this feature already exists, but the interface doesn't exist in FreeBSD. So if anybody wants to actually write some code, the code is quite clearly there in the OpenBSD CVS repository. It's not a large amount of code, So, you know, by all means, take up the opportunity and let's get more of this deployed through the different VSDs. So it's a fully featured interface. So you configure it like you've done there. So that's a /31 that we've got there. So it's a point-to-point interface. There's no point in using /30s. That's the olden days. We've got, you know, the modern operating systems don't seem to have an issue with using a 31. So yeah, that's what we've used there. So you can see the SEC interface is configured there after it's booted up, and you can see how the network mask is configured. So that gives you 2 real IP addresses, which means that you can use things like OSPF and BGP. So it's a fully fledged interface that will, you know, respect Ether frames. And then the OpenID configuration is quite simple as well. So, you know, we use key-based key-based authentication, which makes it a lot easier to push these things out, especially when we touch on Ansible. And it's just, you add an iFace sec0 or sec1, sec2, however many you want after that per server, per client. So the hardware that we chose, we have a good relationship with Lenovo in Australia. So we went with the ThinkCentre M70S Gen 5 small form factor machine. So that is quite cheap for us to buy, and it's also quite available. So we can put an order in and, you know, they're on our doorstep within a week. So it just has an i5 CPU. We didn't want anything, you don't need anything fast for networking. So i5 was sufficient for that. It had the PCI 3 interface for the Intel quad port Ethernet card. Had 256 gigs of SSD. So people go, what about wear? What are you going to do about wear on these devices? I go, the device is going to be in the field for 5 years. At that point, we just pull them out. We don't worry about it. So people get too tied up on wear on SSDs. Just use your SSD. Just enjoy the SSD. Your hardware will die by the time the SSD dies. And 16 gig of RAM, yeah, that's way overkill. You run this in 1 gig, but yeah, 16 gig is like the bare minimum these days. Cheap and available in Australia. We have additional units on the shelf in the workshop, so the team can, you know, run out another one if they need to. And we did investigate ARM and cheaper x86. So you see a lot of home labbers that go to AliExpress or Temu or whatever to actually get, you know, cheap routers. We are a not-for-profit organisation, and we do have international slavery law rules in our organisation, and a lot of those items that you get on AliExpress and that, you can't understand the point of origin for all the parts that go into it. So it was off the table. So, you know, Lenovo gives us a bill and a certificate to say that they know the whole manufacturing stream of their product. So that's what we use. We did have a hardware issue straight up. So the machines ship with Ubuntu 22.04, even though I said don't worry about an OS, it still came like that. The OpenBSD bootloader would come up, but then the kernel would hang on ACPI initializations. Bit of a pain that was. The developers from OpenBSD helped, you know, get around that particular point, but it was just a hack. It was a bodge. It wasn't the correct way of dealing with it. The correct way of dealing with it was a firmware upgrade. So about 3 months later, Lenovo issued a firmware update, and we applied it and go, oh, okay, the project is back on track now. So we were able to kick off. We use the same firmware and pin it across the fleet. We're not going to try anything else. And really, you know, at the end of the day, we will keep these machines in place and then put new firmware on the next iteration that goes out. The network stack. So I touched on LO1. LO1 gives us the ability to do NAT on the external interface. So it doesn't matter what IP address the external interface has. We're fine. It's the source of IPv2, and it's also the router interface for OSPF loopbacks. So what we do is announce loopbacks throughout our network and use, so all the hosts can find their own loopbacks using OSPF. And then we use BGP peering with route reflectors, and everything connects to the route reflectors from that point. The team is familiar with routing configurations. We do have a couple of team members that come from ISP background, so the whole idea of this particular project was to use the skills that we had in-house and the topologies that they know how to use. So that was key to this particular project. And what it also did meant we could remove the overlays operating over IP2 VXLAN, for example, here. I touched on the netting to egress, and then being a WAN interface with changing IP addresses is fine, means we can swap that out to a 5G dongle. And we've already touched on the DHCP pleased. Again, that's a great thing, use it. We moved the syslog output from UDP to TCP, and DHC relay duties were moved downstream into the layer 3 switch. So our layer 3 switches are just fs.com switches, and they provide a full stack without the expensive Cisco licensing, so we can utilize OSPF and BGP on those switches, no problems. And it meant that we could simplify PF so it's more generic. So we wanted a PF installation that was across all of the machines across the whole environment to operate as one, so then that way we could not have, you know, boutique configurations here, there and everywhere. We wanted to have one rule set that ruled them all. So we had to come up with a universal configuration. So universal configuration, everything is in OpenBSD in multiple conf files, bgpdconf, ospfdconf, pf.conf. That's good, but it also has a feature called include. And include is an awesome feature, and I highly recommend using it more often. What that allowed us to do was create a centralized conf.log local configuration file that could be then used for specific configurations for that machine, so then that way you're not having to modify multiple different files for every different machine. You just have one conf.local file, and all the other files are generic and will read in that conf.local file to fill out the variables that you use within your configuration. So this is an example here. So obviously your conf.local has to be 0600 root wheel, otherwise you will get things like BGP and PF complaining that things are not so right. That's a permissions thing. I can totally understand it, and it's fine. So we define our interfaces, and then some key points that we need as part of the actual configuration here. So we've got where the hub is, which is Terminator 01 in this example, and then you've got your site in this example where that's the loopback for that site, so then that way the Terminator knows how to, and uses the source ID address. We have some other things like SNMP configuration that's in that conf.local, and obviously your OSPF, your area ID for OSPF, your BGP ASN, and your neighbors that you need to communicate to, and whatever BGP networks that you've got actually running on the host. So let's look at some of the includes that we use in BGP. Now these are stripped down, they're a little bit bigger than this, but it's really just to give you an idea of how the include gets loaded and the variables get fleshed out as part of the reading in process when the daemon starts up. So we've got, you know, the ASN, the router ID, what networks there are, and I mean the neighbors, they don't need to be declared because those route reflectors are never going to change, so that's fine. And then you obviously your network prefix set. OSPF is similar, nice and small here. You've got your OSPF ID, which is usually just your loopback ID, and then your area that you've declared and the connections that are part of that area. PF. So what we've got is we've got quite a few configurations in separate files within inside PF, but you can update those files, but PF will not recognize them as changing. So part of Ansible, it will check to see if PF has changed and then reload PF. Problem is that if you're changing one of these other files like block list, for example, the PF file doesn't change. So what do we do to get around that? We use version tagging at the top of the PF file. So anytime that anybody touches any of the files that are related to PF, they have to increment the version number. And then by that, when it does a PF reload, it goes, oh, yes, there has been a change in PF, and it does a reload, a check, and then a reload. Automatic builds with OpenBSD. So we've got an answer script that's on a web server, and then the root key that's sitting there, so a root public key. We don't worry about having any keys like for particular users on this machine, and we allow permit. We permit root login, but it needs a key base. It's not using permit root yes, so it gives us layer protection. But PF is tightly protected by SSH is tightly protected by PF, so it's only a couple of IP addresses that can get to it anyway. So we do a prerequisite on the builds. So we do an Ansible playbook, new host, and we install some packages. So this is to prime a freshly built host, and you need to install Python 3 and gtar basically. They're the two packages that we know that we needed to put, and you need to execute that with a raw command inside Ansible to get them on the machine, ready to go. Once they're on there, everything's fine. You can go back to using declarative states with Ansible. So here's the unique settings where we copy different unique settings across. This is just a subset of different things. So the conf.local goes across. We set the mode and the owner and group as we go along, just to ensure that we force that. So we've got unique and then inventory host name. So when we select a host name to actually push this out, there's a directory structure that's created underneath unique / firewall1 / etc conf.local, and there's all the other hosts like that. That goes out to each host, and then that way it keeps unique. OpenID, we pull back the pub key so it can be put into the hub. And this is where we modify some system files. So we look at FSCK. So by default, FSCK in OpenBSD just does a preen at startup. However, we've found that if you have quite a few power outages, that's not really stable. So what we've done is using FSCKY and just force FSCK every time it starts. It doesn't matter. These machines have only the base system on them, so they are fast. We do some changes in SSH, obviously. We set up our change in the syslog to use pointed to our syslog ng server. And then we restart with handlers. So we do some notifying there, and then it goes through the handlers. So restart syslogd, restart sshd, and etc. Then we've got PF. So as part of our rules updates, we've got a hard block rule that has a bunch of IP addresses or subnets that are of different persuasions across the world, just basically to block those. So then we've got the pf.conf, and then, as I talked about earlier, we've got pfctl-f. So what that does is it does validate when it copies the pf.conf, because it'll always change because of the version number change, and then it'll reload pf. And then we load some custom patches. So we do track patches outside of the tree because some patches don't end up in the OpenBSD errata. So we do have our own build service, and it's usually around the SEC interface or some issues around SNMP or whatever. We've had particular issues, but we have a build chain that we can do that. And here you've got, we untar, it's not very elegant, but it does the job. We also reorder the kernel and then wait for the kernel to finish doing reorder. We found that it just skips past it and just starts rebooting the machine before the reorder's finished, and it causes us nothing but issues. So we do have a wait now. And reboot after applying patches. And that's basically the reorder that we do. Touch a file, and once the file has been done, then reboot. Syspatch the servers. we basically syspatch the servers with Ansible, so we don't actually have to log on the machines. There's tasks that are built based into Ansible that supports a wide variety of OpenBSD commands. We've got sysupgrade, so that does the change when we want to kick up the version from 7.4 to 7.5. It just pushes out the fleet, and it's just like you just see a big list of machines that say they're updating, and it's like you'd sit there going, oh, but it does come back. So I've never had an issue with the sysupgrade path. But you do have to do some important housekeeping after that because the ABI changes frequently inside OpenBSD, which means the previous version of Python may not work on the newly updated system. So you have to do a force raw for the package upgrade for Python 3 and GTAR. Then we touch on upgrading to any other packages that might be on the machine, upgrade them all to the latest, and then clean up orphan packages. So where packages are no longer required because the machine has had its update and a dependency is no longer required, removes that dependency. The end product, that's just we have 25 of those around the state, and that's basically it. We've got the network connection from the ISP, and then we've got the ThinkStation. There's a couple of other Lenovo ones in there for test purposes, but that's because that's my lab in my office in Melbourne. Yeah. So conclusion, building on past experiences, we were able to reiterate on our device into an ephemeral appliance. It is brilliant. It's like, we are really happy with it. We leverage newer and more supported OpenBSD technologies, specifically Sec0, or Sec4, OSPF and BGP. BSD continues to be a valuable asset to our organisation, and I can't emphasise that enough. Thank you, thank you, thank you. And indirectly, BSD has assisted in providing better services and outcomes for our clients and staff. Special thanks goes to David Wen from OpenBSD, the OpenBSD project, and everybody here that works tirelessly on open source software. Please donate. Thank you. Questions?
Eddie? Yes.
Hello, could any other OS handle the networking you've done in place of OpenBSD?
Could any other OS handle the networking besides OpenBSD? I think FreeBSD could do it quite fine. And there's nothing here that's unique. The Ansible stuff for FreeBSD is good. It just requires a SEC interface to be built into the kernel.
For the management bit, apart from Ansible, have you looked at any other choices?
So I've been down this path for quite some time, and it's been on my to-do list for building, Ansible-like stuff, so Salt, Puppet, and things like that. Ansible was simplistic when I started it, and there's a lot of documentation, very good documentation online. So it was a no-brainer. It was simplistic and integrated well with the product that we're planning to use, OpenBSD. So we're really happy with it. There's just no need to have any more complexity than we need. Yeah, we did. We looked at Salt, Puppet, and all those sorts of things. Yeah.
Any more questions? Yes.
Hi, great talk, by the way. Am I right that you're pulling all the traffic from your branch offices to the hub, or will you push it to the internet locally?
Only internet. So the question was, are we moving all the traffic through the hub into our main office? No. So where people are using, say, Teams or something like that at that branch office, they'll go straight to Microsoft from the office. It's only internal services like the Microsoft patching services, phones and things like that, intranet things, that's all that goes over the hub. So, on a normal busy work day, we're probably looking at about 15 meg per site on a sort of a continuous basis. But yeah, you know, during patch upgrade, yeah, it'll go, sky's the limit. Just tap out the 100 meg link, no problems at all.
Any more questions? Should we thank Jason? Thank you.
Thank you, everyone.
Yeah. Hello, 1, 2, 3. 3, 2, 1. Is it working? 1, 2, 3. Hello, hello.
No, I can see. I can see it. But not hear it.
Okay. Okay, it's working.
Yeah.
Okay.
Test. Yeah. Okay, our next speaker is Hans-Jörg Huxer, and he's going to tell something about confidential computing with OpenBSD, and give him a round of applause, please.
Okay, thank you very much for the kind introduction. To be honest, it's the first time in years that I'm doing a talk like this, so bear with me when I'm a little bit nervous maybe, and if you don't understand me, let me know if I can improve it. So what I want to talk about today is confidential computing with OpenBSD, and maybe yesterday I changed my mind a little bit, and maybe we are talking about confidential computing with VMD actually. But let me introduce myself shortly. In the mid-2000s, I have been actively developing with and for OpenBSD, mainly in the IPsec area. IPsec CTL, I think, was written by me. ISA KMBD, I was involved in stuff like this. My first experience with OpenBSD is actually OpenBSD.5. I think this was 1996, something like this. And since then, I'm working for a German company, Genua, that is mainly building firewalls and VPN applications based on OpenBSD. So my daily work includes mainly developing on OpenBSD. So confidential computing, what is this all about? To me, it was a buzzword, to be honest. And some time ago, maybe last year, beginning of last year, at our company, at my day job, the term confidential computing kept popping up, people talking about it. So I got interested and was wondering what they are talking about. And I was hearing some claims like from customers that they want to work with confidential data in a public cloud. So public cloud, what does this mean? So to me, this means mainly something with VMs, virtual machines. And the problem that these people seem to have is that they want to work with sensitive data in an untrusted environment. You have a public cloud provider, and you sort of have to trust the cloud provider. And then on the other hand, there are people that provide VM service to customers or to projects to host their project on a virtual machine. And these people have a similar problem. If you want to use your SSH private key in that virtual machine, you sort of have to trust the hypervisor. You have to trust your VM hosting environment. And obviously, in that area, there's a supposed solution that is called confidential computing. And some slogan I read some time ago was something like this: turn public cloud into a private cloud. So this is a bold statement. And I started thinking about this. What do they mean? What does this mean? What do they want actually to achieve? So let's look at an untrusted environment. Everybody I think knows this. We have our hardware. We have an operating system running on top of our hardware. And do we see the mouse pointer? Yes, here it is. And we have some userland process running on top of the kernel. And we all know sort of the kernel has all the privileges. The kernel controls the resources, including the memory used by the userland application. Therefore, we have to trust the kernel because the kernel can peek into our userland application. And similar, the kernel provides some isolation between other userland processes. So we sort of hope, we should hope that we can be sure that one process is isolated from the other process, but nonetheless, both processes have to trust the kernel. And when things go severely wrong and the kernel has a bug, an evil application, of course, can trick the kernel into exposing information of the other process, including the memory of the process, including, for example, if this would be an SSH agent holding a private key, and if I can trick, due to bugs, the kernel into exposing these private keys, then the keys are gone. Now, with virtualization, we have sort of a similar situation. Now we have our hardware. On top of the hardware, a kernel is running, a hypervisor is running, and that is providing an environment where we can run our virtual machine. And now the situation is quite similar. The hypervisor is privileged. He controls all the hardware. He controls all the resources of the machine. And the hypervisor can peek into the memory, memory of the virtual machines running on top of the hypervisor. Again, the hypervisor provides some isolation between virtual machines, so they are separated, similar like the processes. And as we learned yesterday, OpenBSD and VMD using privilege separation to really make the chances really low that a bug in the hypervisor might allow, does not allow or reduces the risks of some guest exploiting bugs in the hypervisor to gain information about some other guest. So this would be the one scenario, that VMs exploit each other, and the other thing is still we have to trust the hypervisor to not leak information about the virtual machines. And now in these untrusted environments, confidential computing seems to provide the claim that it's possible to protect the address, the memory used by the virtual machines by, for example, encryption, and therefore that the hypervisor does not need to be fully trusted anymore, because the hypervisor now only sees encrypted memory of the guest, and each guest has its own encryption keys. So even if one guest is able to look into whatever reason, gains access to a page of another guest, he only will see the encrypted memory of that other guest. And this obviously needs, this needs some support, this needs some support by the hardware. Because to get the hypervisor out of the loop, that the hypervisor is not trusted, all this encryption of the memory has to be done somehow, done somehow by the hardware. So to summarize, confidential computing makes these claims that it provides techniques to keep data confidential. This is a difficult word. Difficult word. To keep data confidential. I think that's what I want to say here. And that it also keeps the integrity of data. The data cannot be modified. And it also claims that it provides mechanisms to guarantee some integrity of code. Code that is working on the data shall not be modified somehow by some attacker, by the hypervisor, for example. So there are several levels, possible levels of isolation involved. The most fine-grained level might be something like isolation on function or library level. A little bit more coarse-grained, it is isolation on the level of a full application. And what we are looking, or what I started to look into, is this most coarse-grained level of isolation of a full virtual machine. So for example, with the application isolation, you might know that the Signal app on some iOS phones and Android, I think also, they use enclave technology to store the private keys used for the communication with Signal encrypted in that enclave. And only inside the enclave the keys are visible, outside they are not. So this is maybe on this function or application level isolation. And this is more about enclaves and stuff like this. What I started to look in is on the level of a virtual machine, which is a much larger thing than just an enclave. So as I mentioned before, this is not possible without support of the hardware. And hardware can provide many mechanisms to support this. One mechanism is runtime encryption, and that is the one what I am looking into in the context of the virtual machines. Other mechanisms are stuff like attestation. This is about to verify or to guarantee that your virtual machine and the code you're executing is a defined state, that you're actually running that operating system and that application you want to run and not something else that got modified by someone. Maybe if you're familiar with concepts like secure boot or measured boot, this is something similar like the attestation mechanisms that are supported by confidential computing. And then there are more mechanisms to guarantee stronger isolation, but I think this is mainly regarding integrity of memory, for example, integrity of binaries, but I'm mainly looking in the runtime encryption, and actually only in a specific aspect of the runtime encryption. So, the hardware has to provide some support for this. And what I started to look into is actually the secure encrypted virtualization provided by AMD CPUs. Intel has something similar, something different. They call it TDX. I think this is Trusted Device Execution Extensions, something like this. ARM also supports, or upcoming ARM architectures are supporting something they call ARM CCA, that's confidential compute architecture. And this is all focused basically on virtual machine, confidential computing for virtual machines. Some other thing you might know is Intel SGX. I think this was software guard extensions, something like this. And this is more an enclave thingy, meant to run a library or functions of a library within a safe compartment. And I think the original idea was more from the DRM world, digital rights management, so that you can run your DVD decoder inside that compartment without leaking the secret key.
That's how it's supposed to work.
Sorry?
That's how it's supposed to work.
Exactly. I will have a slide about that. So, to summarize, what I got interested in is building something like this with OpenBSD. Yeah, using AMD SEV technology, and I only focus on the encryption of the memory. What I cannot encrypt right now, what I'm working on is to encrypt the CPU state. This right now we cannot do this. It's only about memory encryption. It's not about integrity. So there are limitations, but my main focus is actually to learn about this. Just by doing it, trying it out, and then we will see if things work or don't work, and then we can see what we can do with it. So here is a very simple sketch of a modern CPU, modern AMD CPU. What we have, the gray box is the die, the chip, the thing that represents your CPU. And within the CPU, we have multiple cores. And at somewhere on the chip, on the die of the CPU is a memory controller that allows the cores to access the DRAM of your machine. And AMD, into this AMD hooked their framework, their technology for secure encrypted virtualization. What they did, they introduced a new component on the CPU chip, the so-called platform security processor, PSP. Maybe they call it now security processor, SP, I don't know. I'm using the name platform security processor and the short form PSP. And the PSP is actually a small ARM5 CPU sitting next to the CPU cores, and it's running a little, how do they call it? I think they call it TrustOS, a little operating system that is basically doing key management. Key management. What for are they doing key management? Okay, here's the mouse. We have the memory controller, and they included in the memory controller an AES engine for doing AES encryption with basically line speed. So they say it's super fast. This means when, for example, the blue core is using a memory encryption, and when the blue core is storing data to the DRAM, the memory controller will encrypt the data that is coming from the blue core with a specific key specific to the blue core, and will it store encrypted in the memory. And for the other cores, and each core is actually using its own key. Not only each core, each VM that is running on the core has its own dedicated key. So you can run multiple VMs, and all VMs will have their different keys. In that picture, I think it's 2 VMs, a blue one and a red one, and they have the blue and red key. And the other way around, if the blue core is accessing physical memory, the memory will be read back from DRAM, decrypted, and loaded into the caches of the CPU. So, and the key idea here is that the actual guest is controlling the encryption. What does this mean? The page tables used by a guest, the guest page tables now use an additional permission bit within the page table entry, the so-called crypt bit, C bit. And with this bit, the guest can control whether data mapped by the guest page table is to be encrypted or not. If the data is encrypted, the data is private. It goes to the DRAM, and only the guest VM itself can read it back and decrypt it. If the C bit is not set, then the data is public. It will not be encrypted and will go as plain text to the main memory, to the DRAM. And with this, it's shareable between the guest and the hypervisor. Yeah, and this is a sort of a departure from the original x86 security model, where now the privileges of the hypervisor, that is, or the operating system, is diminished, and the guest gains more privilege. This means, meaning the guest has a control and can decide whether to share data or not to share data, to encrypt data or keep it in plain text. And this is, I think this is a new concept they came up with. And how does this work? Now I need the mouse pointer again. Or maybe not. Here it is. Okay, what do we have here? Consider this example. We have our CPU. Just for simplicity, there's only a core. The other cores we do not care right now, and that core is executing a guest, the red guest that is identified in this table. AMD uses the term ASID. It's an address space identifier, and each virtual machine guest is assigned a unique ASID, and each guest is identified by this ASID. So right now, we are executing the virtual machine, the guest, with the ASID 2. In its memory, there's some text, there's some heap, there's some stack. And that stuff is all encrypted. Now, when the guest is accessing a virtual address because the guest is just running a normal OpenBSD. OpenBSD uses virtual memory, virtual addresses. So when the guest accesses a virtual address, this address needs to be translated from the virtual address to the guest physical address. AMD, and I think Intel also, they use something they call nested paging. This means the guest is maintaining its own page table. And this page table is also encrypted within the memory of the guest, so it's not visible to the hypervisor. And what the guest is doing, he's translating, or the CPU is by reading the guest page table, translating the virtual address to a guest physical address. And this guest physical address, again, is translated by a second page table, the nested page table, that is maintained by the hypervisor. And this hypervisor maintained page table is actually yielding the actual physical address. The actual physical address addressing some memory in our DRAM. The new thing now is about the script bit. When in this example the page table entry is marked that this virtual address, that this translation should yield an encrypted translation, the CPU will remember the crypt bit and say, okay, this will be an encrypted memory access. And then the physical address that was yielded by traversing the nested page table is modified. AMD decided to reduce the physical address space when you're using memory encryption. So actually, we always have 64 bits addresses, but AMD decided 20 years ago, 10 years ago, that there will only be 52, I think. The upper 12 bits of the physical address are always 0. They will not be set. So we only have up to 52-bit of physical address space. In practical implementations, I think it's, if you buy a main board, then I think it's 44 bits, 45 bits, something like this. So you can put, I don't know, many terabyte DRAM into that machine. Now, when you're running with memory encryption, some of these bits are repurposed. Of the physical address bits, they are taken away, and they are now repurposed, one for setting the crypt bit. And in that picture, we have the crypt bit at the position 51, counting from 0, and this bit is now set because the page table, the guest page table, had the crypt bit set. So now basically it's forwarded into the actual physical address, and then here, and then also the ASID, the address space identifier that is identifying that particular VM, is also patched into the physical address. Here in my example, here, I cannot do this. In my example, I reduced the physical address basically by 8 bits. Here and here, so I reduced it from 52 to 44 or something like this. In reality, it's actually more like 4 or 5 bits, but then the number 2 wouldn't have shifted and the picture wouldn't be so good. So now from the core, we get this physical address forwarded to the memory controller. So, and the memory controller now realizes, okay, we are doing memory encryption here. So the bit 51 is set. This means this access must go through the encryption path. We have to, if it's a write to the memory, we have to encrypt the memory. If it's a read from memory, we have to decrypt it. And he also knows, okay, we are using the ASID2, so that's virtual machine number 2. And here we have a table, and that table is actually built by this PSP, by the platform security processor that provides that generates the keys and stores such a table in the memory controller, and the memory controller look up, okay, for the AC2 we use that particular key, and now the memory controller can do the memory access and encrypt or decrypt the data. So, to make sure, within the core itself, the data is in plain text. In the cache, in the memory, and in the level 2, level 1 cache, all the data is in plain text and is sent in plain text to the memory controller, and from the memory controller leaving the CPU, leaving the component CPU, to the main board, to the DRAM, the data is encrypted. So on this path, we always see the encrypted data. Within the CPU itself, it's not. Another thing that is not encrypted with this technology is the actual CPU state. Somewhere in the CPU, we have the registers, the instruction pointer, stack pointer, the flags, and these are also not encrypted. So at some point, the hypervisor, when the guest stops and is exited and the hypervisor takes over, the hypervisor sees the actual CPU state. So the hypervisor knows the instruction pointer, the stack pointer, the flags, and so on. And if you consider using AES and I, for example, hardware encryption instructions of the CPU, the AES key used for the encryption is stored in the floating point unit in the FPU, because the AES and E is implemented basically by the FPU, by the floating point unit. So when the guest exits and the hypervisor takes over, the hypervisor also can see the FPU state. This means if you're doing AES and I, then the hypervisor still can see your AES key that you are using. And if you're doing IPsec, for example, then I'd like to take questions afterwards, okay? So, and then I think this needs to be remembered. The CPU state is not encrypted right now with this basic SEV technology. So that are some of the limitations I came along. The CPU state is not encrypted. Right now there's also no integrity protection, and this attestation also has some limitations. AMD provides further levels of this technology. SEV-ES, that's encrypted state, that is all about encrypting the CPU state. But this is the next level. I'm working on this, but it still needs to be done. And then there's also a next level that is called SEV-S&P, secure nested paging, that provides more more integrity. And we had a comment about the security. So there is a bunch of, I think these CVEs are quite recent. So if you don't update your firmware, your VMs will leak memory and you can decrypt stuff. There are people that were able to hack the platform security processor to extract the firmware, to load a different firmware on that PSP. The PSP is doing the key management, so this is not so cool. But right now, I do not care about this, because I want to figure the things out, and I hope in 10 years all these bugs are fixed by AMD. And my goal is to build a confidential VM on OpenBSD and basically learn from it. Why OpenBSD? Okay, I'm using OpenBSD since 20 years with VMD, VMM. We have a great virtualization platform. I read the code, I sort of understood it. And I think, okay, I will use this to implement confidential computing using these AMD technologies with OpenBSD on OpenBSD for OpenBSD. And my main goal was, in the beginning, to keep it as simple as possible. So, the big picture, what needs to be done to actually launch a virtual machine using SEV and memory encryption. We have the VMD. VMD is the component that initially loads, where's the Mauszeiger? Here. That initially loads the kernel image into the guests into the guest address space, along with some stack, along with a page table. Then VMD builds the CPU register state. Whoops. For example, the instruction pointer needs to point at the first instruction of the kernel. So when you start the guest, that it starts executing instructions from the first instruction of the kernel. So, and all this is written to memory. And with a non-encrypted virtual machine, that's basically all that, I'm hugely simplifying here. That's all that need to be done to start the virtual machine. There's a special there's a set of special instructions in the AMD instruction set, something like launch VM. Then all that state is loaded and the guest is executed. If we want to use AMD SEV, we have to do an additional step. We first have to encrypt all the image that we want to execute. This is why, something I didn't mention yet, that when you enable SEV in the virtual machine, all instruction fetches go through the decryption path, regardless if the page with code instruction is mapped as with the decrypted or without. If it's an instruction fetch, it always goes to the decryption path. This means the initial image that we are running needs to be encrypted by VMD. And this is done with VMD talking to the platform security processor, instructing the processor to generate a new key to associate that virtual machine guest, the ASID of that guest, with that particular key. And then the PSP has to read all memory or all the pages that are used by the guest, has to read it, has to encrypt it, and write it back to memory. And then when the guest is launched, it can start executing, fetching the first instruction, and this gets decrypted again, and the instruction can be executed. So, to get things going, what do we have to do? We have to implement a driver for this platform security processor. We have to modify VMD to talk to the platform processor to encrypt the kernel image, to build the page tables using the C-bit, stuff like this. Then we have to modify the VMM driver, that's the in-kernel part of the hypervisor, to actually enable SEV. When he launches the virtual machine, there's a virtual machine control block, and there you have to say, okay, this guest should run with SEV enabled. And then we also have to modify the guest kernel that is running, because the guest kernel should use the decrypt to encrypt all its memory. The guest kernel is building page tables, and he has to use the decrypt to make sure that the guest is encrypted. So my plan was sort of make it as simple as possible, just focus on booting the RAM disk kernel. I do not care really about devices. A RAM disk kernel does not need a disk. It's just running out of a RAM disk. I will fully encrypt that guest, not caring about DMA or something like this, because with DMA we have to talk to the hypervisor, and we have to share memory with the hypervisor, and therefore we have think about, do we map this page, encrypt it or not? I do not care right now. I encrypt everything. And this sort of works because because the main hardware components that need to be emulated by a PC platform that is emulated by VMD is a handful of chips: timer chip, real-time clock, interrupt controller, and the serial console. That one is interesting for me because I want to see something. So if we can access the serial console, then I see something and I'm not blind. And this is all done with in-out instructions, with programmed I/O, and not with DMA. So my idea was, so this actually should work if I encrypt everything. If I use everywhere the hard bit, C-bit in the guest, if I hard code it, then it should work. And this was the plan in last year, December. So I started with implementing minimal support for this platform security processor. There's a bunch of commands you need to use to encrypt, to initially encrypt the guest memory. That's the so-called launch protocol. And this is doing this red arrow here. And I needed some more commands. So we can skip this. Then I had to modify a little bit with VMD. I only use direct kernel exec, so I'm not loading a BIOS. I'm not going through real mode or something like this. VMD allows to directly execute the kernel image you want to run. So it's basically ELF loading and executing. And VMD also has to modify, has to use the pcrypt, the C bit in the page tables, so the memory is actually encrypted. And then VMD has to talk to the PSP, please encrypt everything. The modifications for VMM were quite simple. Basically, in the configuration block, you have to say, there's a bit you have to set, and stuff is sort of working. So in the guest kernel, I also defined a crypt bit, and on my machine, I know it's bit 51, but AMD says, yeah, this is implementation specific, so on some CPU, it might be different. So you should actually figure out what bit you are using, and I just hard-coded it. And then, of course, in the PMAP module, where you're setting up the actual mappings, I was also hard-coding the C bit. And with this, it was actually possible to boot RAM disk kernel. It actually also saw some stuff of the virt.io devices, but yeah. But this took about 2 months to earlier this year. So in the round 2, I was working, but because my second goal was then I want to use the same kernel as guest and host. Before I had a modified host that could run encrypted guests, and I had a modified guest kernel that was able to be run encrypted. So to just use a single kernel for both purposes, the kernel has to detect, am I a guest or am I a host? Am I using encryption or am I not using encryption? And depending on this, he has to be more flexible about defining the script bit. So I cannot hard code it anymore, and that's what I did. So the next thing that we should do, we want to do DMA, we want to do virt.io. And this is only, in my first approach, I just did a hack to map everything unencrypted that is using the BusDMA MEM API, so all memory used by, for example, MBus would be unencrypted. However, this is not really working. It was working, but this is not what you want to do for some reasons. So therefore, I needed to implement something like bounce buffers. This is a thing that is quite old. It's from, if you have some old ISA hardware that can only address below 16 megabyte physical memory, then you also need bounce buffering, copying stuff from high memory into the low memory and back and forth. And the API is there, so I modified this that by using these bounce buffers, that the bounce buffers itself are mapped unencrypted, so they can be shared with the hypervisor. They show up unencrypted in the hypervisor. And the BusDMA API provides a function that is called BusDMA map sync or something like this, that is actually doing the copying. On the original PC platform, it doesn't need to do anything, this sync function. On, for example, on some other platforms like Spark, it is needed to implement flushing of caches and stuff like this. So the hardware is DMAing into memory, and before accessing that memory, caches needs to be flushed. Or the other way around, when the CPU writes stuff to the memory, and before the hardware can access its caches needs to be flushed. And this is implemented by the sync AP, and I am using it in a similar way just for copying back and forth between the encrypted and non-encrypted memory. And with this, We can skip this. We can skip this. Yeah. And with this, it was basically possible to just use virt.io. And then there are some optimizations I want to skip. So now, earlier this year in May, I got this sort of finished, and now I could use the same kernel as guest, as host, and the confidential VM was sort of working, almost, because there were bugs in the VIO, 5 minutes, thank you. And in the VO blog, I got crashes when doing a build. Nonetheless, I mailed a diff out because we are doing open source. So it's important to get people involved. I showed the diff around. And a colleague of mine, Stefan Fritsch, did some debugging in the virt.io, and we got these crashes fixed. Alexander Blum was doing testing and debugging of this DMA bounce buffer stuff that I did. Then I also got input from Dave Vitula, thank you, and from Mike Larkin, Ketenis, and so on. And we got the stuff committed. And right now we have sort of a stable VM that survives a make build, and the memory is encrypted. Is it? So to really figure this out, we can skip this and look at this. I decided I need something like a heat map. I want to examine the guest physical memory and see if that memory is actually encrypted. And from this, I modified the VMT to get a dump of the physical memory, and then I plotted this heat map. So here's the lowest address. I think that's a 1 gigabyte machine. So here we have address 0. There is somewhere 1 gigabyte, and it looks like I would expect here in the lower part. We have the initial kernel. We have the kernel text image. Above it are the initial page tables. Very on the top, we have stuff like the DMISC buffer, and in the upper range, that's memory. This is actually used by the guest running. So this is when you are using a guest without encryption. That's the picture I got. Now with SEV enabled, what I did, I was compressing the pages. I dumped the memory, compressed the pages, and if the page was easy to compress or good compress, then it's not encrypted. Then it's compressible data. And with memory encryption, I got something like this. We see that the used pages are hard to compress. That's a darker green. The lighter green or white means easy to compress. So the memory used by the encrypted machine was hard to compress. So I think I was confident that we are actually running encrypted. And then I did 2 minutes left. I did a little hack. There's a so-called zero thread in the kernel that is nulling pages on the free list. So and usually this thread just is maintaining 20% of the free memory being nulled, being written zeros to. So I modified it that it actually zeroes out everything that is on the free list. And so I booted the machine, waited a minute, shut it down, dumped the memory, and I see that basically all pages got touched by the, or most of the free pages got touched by the zero thread. So I assume they were encrypted. So what have we accomplished? We have the simplest version of SEV enabled as an OpenBSD guest on a host. The stuff is committed. Next steps would be the state encryption, fixing all the bugs. I guess there are plenty of bugs left. Optimize DMA, there is stuff that can be done. We haven't talked about performance. There's stuff that needs to be done. We haven't talked about this attestation, about this secure booting stuff. So there's stuff that needs to be done. And there's even more stuff to be done. So that's what I have to tell. I just want to say thank you to some of my colleagues that helped me with the slides, Mia Teschauer and Jan Klemko. He's also working on OpenBSD. And Alexander Blum and Stefan Fritsch for debugging and committing. And I'd like to thank the people at Tech for their input. Thank you. Questions?
There's room for a couple of questions, so.
So the latest AMD 64 CPUs can have a 57-bit virtual address space. So what prevents them from using traditional shadow paging in a hypervisor to fake SEV?
The answer, the question was, it's recorded? Okay, then I don't have to repeat it. I cannot answer this. I do not know. I'm still in the beginning of figuring things out, so I do not know. Yes, there was a question by René, I think, earlier already.
Does the is the cache memory of the CPUs also encrypted?
No, the question was if the cache memory is encrypted. No, in cache we have plain text. And only going out to the DRAM, leaving the CPU, the die, that stuff is encrypted. So I hope, also if you think about stuff like Spectre Meltdown, I don't think this will help with encryption.
Is this the first open source hypervisor that?
No. With Linux, you have KVM and QEMU that they can do this.
They already do this.
They already do this.
Thank you.
So what happens when you reconfigure cache set arrays to use as scratch pad memory? Do they get invalidated before you get to inspect them? Because this is needed during early bring up of a memory controller for training.
I cannot answer this question. Again, a specific detail, I do not know. I'm sorry.
Okay, last question.
Yeah.
You touched on performance at the last point in the slides. So what is the overhead of encryption?
That's a good question. So AMD says it's 1% or something like this regarding the memory access. And as far as I know, they're encrypting anyway the memory. If you do not configure anything, then they put in a random key. And so it's easy to say there's no penalty when you use encryption because you're using. I might be wrong here. If someone from AMD has some here in the room has details, let me know. And with regarding Alexander Blum is doing some tests and the performance is degraded, I would say. Is it horrible? No, but it's not good.
It's mainly the bounce buffers.
Yeah.
So I don't test this encryption thingy. I just enable the bounce buffers.
Yeah.
And that, of course. Thank you. So I haven't tested. I didn't put the encryption machine in my automated test setup yet, but I have added a thing that I can just set a flag to force bounce buffering, even on a non-encrypted thing. So that helps a lot to find bugs in the drivers. If there's some BoostDMI sync missing, and with that alone, I get a decent performance degradation, like 30%, 50%.
And there's room for optimization, but we will see next year.
Okay.
Thank you very much.
Thanks again.
Sure. Background so I can kind of explain the problem space and describe what the goal of the software models at the end are talking about. So the first thing I want to talk about is what are buses and bridges? And so it sounds kind of very basic, but we can think of computers as being that computer systems contain a lot of different components, things like processors or memory or I/O devices. And those things need to be able to communicate with each other. And so we connect all these components inside a computer system using buses. So traditionally, it's like actual wires that we send signals over to allow communications between devices. Nowadays, some buses use wires and some buses are not because it's all contained in one IC. And then, so that's kind of talks about what buses are. Buses are a channel to allow different components to talk to each other. Well, bridges are a kind of special device that are connected to at least two buses, usually kind of two different buses, and they allow messages to flow between different types of buses. So we can pass messages to components that aren't directly connected to each other, but kind of across some kind of hierarchy or path. And so bridges can forward requests, and in some cases that might need to translate or modify the request as it's transiting the bridge. And traditionally, in a computer system, these components that we can think of, they're basically organized in some kind of hierarchy, some kind of tree-like structure. So here's a picture, and somewhat abstract, of what a device hierarchy might look like in a computer system. I mean, I know in some cases on modern CPUs, a lot of these things actually get shoved into the package, and so it's not quite as cleanly broken out as this abstraction. But at the top, we have a couple of processors. We have some memory that they're connected to over some kind of system bus that connects CPUs directly to RAM. Then we have some kind of I/O controller that's going to deal with DMA requests from devices and kind of allow access from the CPUs down through the I/O controller out to I/O devices. And those I/O devices are connected via different types of buses. So in most, at least like the x86 systems that we work with, that first level I/O bus is going to be a PCI Express bus. And so then it's got PCI devices as children of that. And some of those devices, you might have PCI bridges that we'll talk about later, but we also have other kinds of bridges in a way, well, logical bridges that you might think of. Something like a SATA controller or a USB controller that allow you to communicate over a different type of bus on the back end. So a SATA bus is very different than a PCI Express bus, for example. And yet, those controllers do kind of provide a way that a CPU can send a request down to a SATA disk, and it crosses all these things. So then, part of my title was managing resources in bus drivers, and we've talked a bit about what buses are and bridges and kind of special devices those are. So what kind of resources am I talking about? Because there's all sorts of resources that operating systems manage, especially if you've been to any CS undergraduate OS course, you talk about all sorts of resources. And we're not talking about things like CPU time, we're talking about a few very specific things. And two in particular that I'll kind of probably talk about most. The first is devices have registers. That's how you configure devices and control devices directly from the CPUs. You read and write registers, usually using memory mapped I/O of some sort. So being able to control access to those registers, maybe being able to decide where those registers live in your memory address space. That's one of the kind of resources a bus driver will manage. And the second one are interrupts. So I, as a device, want to be able to interrupt the CPU. So I'm connected maybe logically to a pin on the interrupt controller, or PCI has message interrupts, which are another ball of wax. But I have some way of interrupting the CPU, and I need to be able to do that reliably and ensure that I can register an interrupt handler, and my handler gets called when I interrupt the device, and not some other handler or no handler or things like that. So let's talk a bit more about memory mapped I/O and kind of what that looks like, and a bit of what the kind of the problem that we have to address inside our device driver system. So I have here kind of a diagram, and I'll step a bit more, of roughly what the physical memory address space looks like in a kind of typical x86 system. So we've got RAM, mostly, from about 0 up to about 3.5 gig. Ignore old legacy ISA things. Then we have a hole up to about 4 gig for memory mapped I/O. That's generally used for kind of low 32-bit PCI things. Then we have a bunch more RAM, and then maybe at the top of that, somewhere, we have some more memory I/O, and then we have things that aren't even used. So let's look a little bit more detail about the middle region here. So in this middle memory I/O region, that itself is kind of subdivided and shared across different devices. So you might have a big chunk at the bottom, and that's used for the frame buffer for the GPU. And then you might have some other devices like some kind of NIC and USB, and then we have some things that are architectural to x86 to deal with interrupts and interrupt controllers at the top. And then if we drill down a bit further, inside the NIC, we might have a couple of registers, things like the base address maybe of transmit and receive descriptor rings or an interrupt status register. And so in particular, what happens in hardware is if you're trying to read, say, the interrupt status register in your NIC, is you're doing a load restore on the CPU against, well, eventually a physical address. Just pretend the MMU is not here for the purposes of all that we're talking about. So you're going to do a load restore trying to address the interrupt status register. And what happens at the top level is when you do the load restore, RAM doesn't kind of claim the access. Instead, the top level PCI bridge in this case is going to actually claim the access and say, hey, it lives inside my little window between 3.5 and 4 gig. And then that's going to go onto the bus. And then on the bus, the NIC is going to say, the address you passed, that falls into my range. So I, as the NIC, am going to claim this kind of read request. And then inside the NIC, it'll look at the relative offset and figure out, oh, the register you're actually going is my interrupt status register. I'll read the value, and I'll send the reply back. So we kind of have to filter each level down to figure out who does this address belong to. So now let's talk a little bit about bridges and the role they play in kind of what we just described and how we deal with bridges and memory mapped resources in particular. So bridges can use something called a window. And a window is kind of like, well, it's not kind of like it. In a window, the bridge allocates a chunk of address space, usually memory or I/O ports, from its parent, and then it subdivides that address space to hand out smaller chunks to child devices that are behind the bridge. So this is how a device behind a bridge can get access, is that the bridge allocates a bigger window, and it'll claim anything in that window, and then it'll forward the request on to the children beneath it, and then give the children beneath it a chance to claim the request as it passes through. But if a child tries to listen for a request that's outside of the bridge's window, it's never going to see it, because the bridge will never have claimed it from the parent. So the windows claim a region of the address space on the top side, and we subdivide that to hand out things to the children. And some bridges might have to kind of deal with translating the addresses as they go across the bridge. In particular, you heard me mention, I didn't mention it too much earlier, but PCI has this notion of I/O ports, because it's something that x86 has in their CPU architecture, but a lot of other CPU architectures don't have dedicated instructions to access this alternate I/O address space. And so what they do is they take some region of their memory address space, and they reserve that to kind of be a window for I/O ports. And so when you read or write to an address in one of and kind of this specially mapped window, the bridge translates that into a request not for a memory access, but a request for an I/O port access. And so sometimes bridges will do things like that. So let's walk through an example kind of similar to what we talked about before, but this time we're going to kind of think about it as a bridge. So I'm just listing the kind of that little MIMIO region we had before in the 3.5 gig to 4 gig range. But this time, instead of having only devices that directly access that, I've still got the GPU, because it's kind of directly attached to PCI bus 0 in this case. But now we have a couple of bridges. And each bridge allocates a chunk of that memory address space for the devices living behind it. And then I might have a bridge that has nothing behind it. So it's reserved the address space, and it'll listen for requests and send them off into the void where they don't get responded to, or they get responded to with a default, which says nobody cared, nobody listened. Or I might have a bridge with one device, or I might have a bridge with a couple of devices behind it, so that you can have multiple things kind of listening behind the bridge. So that's what the hardware is kind of doing. And so now I'm going to transition to talk about how, and our software device drivers, in particular our software device drivers that are kind of handling buses, how do we deal with that? How do we ensure that the NIC gets a resource that it can use, for example, that is going to get one that we listen to? So in FreeBSD, we have a tree of device objects that we create in a hierarchy. And anything in that tree that has other children is a bus device. So if it is a tree, then basically you have leaf devices and you have interior nodes, and all the interior nodes are bus devices in terms of how FreeBSD talks about them. And that can include things that are physical buses, like a PCI bus. We actually instantiate a logical device or a device T object for a given PCI bus, and other buses like ISA. But bridges are also a kind of bus device, because that's how we represent them. And this is also true in OS 10 actually as well. So we have a separate device abstraction to represent a PCI bridge that talks either between two PCI buses or from the system bus to PCI. And so I should back up a little bit. As I mentioned, a bridge is going to have a parent that's a bus, and it's going to have a child that's some kind of bus. And then we have another set of buses that are these kind of you might call them pseudo buses. They're not correlated with some physical bit of wiring on the box, but it's some way that we can collect multiple logical devices together. So an example of that is we have a top-level bus device called Nexus 0 that's a platform-specific driver. That's the anchor for all the device tree we build for the rest of the system. So we can have several children, but it's not a physical thing. It's just where we start hanging off the top nodes of the rest of our system. And also, for example, ACPI, there is no physical ACPI wires in your system. It's just a way that the firmware can communicate a kind of hierarchy of namespace of its own notion of devices. And we start with the top level of those and kind of attach those to a logical ACPI bus. And the same with Simple Bus, which is used for device tree like FTT and so forth that was used in platforms like ARM. So here's a picture of a non-exhaustive and simplified notion of what you might see inside a FreeBSD system. So at the top, we've got a Nexus bus device. In this case, it's got an ACPI child. The ACPI child has, in this case, at least one child device for a host to PCI bridge. So kind of the anchor of the top of a PCI Express hierarchy. Then we have a logical device that represents the PCI bus below that. That's, like in this case, PCI bus 0. And then we have a couple of PCI devices that are attached on PCI bus 0. So we have the GPU and a couple of PCI to PCI bridges. And I have an error. So there should be a little PCI bus here and here, and my slide would be even harder to read. So I guess ignore this part because I got it wrong. But in particular, notice how there's a bridge, then a bus, then a bridge when we're going across this. If you were to draw this in some other ways, you might only have kind of this. You might not have the bridge, or you might have just the bus. For example, in the ACPI namespace, they don't split these up into two things. And these actually, if you were to look on FreeBSD, both of these would have the same ACPI logical handle associated with them. But we choose to split them up for various reasons and it makes some of the resource management simpler. All right, so apologies that I messed up and I did this graphic today, and so. All right. So those are bus drivers, things like buses and bridges. Now how are we going to manage the resources that we talked about, like memory mapped I/O in particular, inside of these bus drivers? So we need these drivers to provide access to these shared resources to children. So children devices, a device driver pops up and it wants to map its bar so it can read, write some registers. It's going to ask the bus to kind of do that on its behalf. So they're responsible for figuring out how to allocate a resource, if it's fixed or not, or if it's a variable that can be moved around and they need to find the right space to move it around into. They're responsible for all of that. One of the things that a bus driver is responsible for doing is it needs to ensure that when it gives you a resource, it doesn't conflict with somebody else's resource that's already handed out. These systems don't work well with ambiguity. You can't have two devices listening to the same address. It's going to be undefined who wins, or if somebody wins, or nobody wins, or you get a machine check, or something else. So it's up to collectively the bus drivers and the system to avoid conflicts and avoid giving out the same address to multiple things. They also, to function correctly, a bus driver needs to give valid resources. They need to give, for example, when I had the example of the PCI bridge and the NIC was behind the bridge, it needs to get a resource that's in that bridge's window so that if you're trying to access the NIC, the access is going to work and make it all the way down. If the bridge were to hand out an access that's outside of its window, then that resource will never work. So the bridge has to be responsible to hand out valid resources. I mentioned interrupts earlier. We have to hand out what the interrupt resource the device asks for that represents the interrupt it's actually wired to. And that's how we ensure that you can attach your interrupt handler in the right place so that when your device interrupts, your handler is the one that gets executed and not somebody else's handler or no handler. And then once we've actually allocated these resources that are valid, we actually have to let you use them. So if you're doing memory mapped I/O, you need some way to actually map the memory mapped I/O and some way to actually access the registers. And for interrupts, you need to be able to actually add and remove interrupt handlers. So given that these are our responsibilities, now I want to talk about a couple of the abstractions that we have in the kernel for how we deal with these. And the first one is something called a resource manager, which is struct rman in this tree. And rman's role is to describe some kind of address space. You can think of it some kind of thing that has addressable chunks that you can have a bigger, wider address space that you can chop up into smaller regions. So effectively, you can think of it as a special purpose address space manager. We have FreeBSD now, we have several address space managers. We have things like vmem that backed kmem for KVA allocation. When NuBus was first written, we had the specific one for kernel memory, but we didn't have others, and so this rman was special purpose written. And it has some quirks specific, like it'll save references to the devices that allocate resources. So I don't think we could quite replace it with vmem today, but if you were to start writing this today, maybe you would pick an existing allocator like vmem to do this. But this is what we have. So it's special purpose for device resources. And rman can describe a real address space, like CPU physical memory, but it can also describe kind of a virtual address space. So when, for example, for interrupts, we will take the set of interrupt controllers in your system and logically assign kind of ranges of interrupt numbers, or what we call RQs, effectively little cookie values, to all the pins and kind of name them by number of the pins and all the interrupt controllers in your system, and use those kind of names for how we actually, the values of the IRQ resources that we hand out. And so we kind of create a virtual address space out of all these pin numbers for what constitute IRQ resources. The way an rman works is you initialize a resource manager with kind of the absolute max and min of whatever address space you're working with, and then you add one or more regions, which can be a subset of the absolute top and bottom of your address space, but a set of active regions that are available inside the rman. And when you go to allocate resources, it's only going to hand out something that's in one of the regions. So you can have a sparse address space. You could have an address space that says, logically, I can go from 0 to 264, like my earlier picture of the x86 memory address space, but I know that only certain parts of it are actually something you can allocate from. And you'll see maybe some examples of when that's useful later. And then when you're working with rman, if you allocate a resource, we return that resource in an instance of a struct resource object for a single contiguous region of space that we've allocated. And that's what device drivers end up using as their handle for resources. And one of the things RMAN does is it takes care of avoiding resource conflicts. So if you try to allocate something from RMAN, it will fail if you do a request that it can't satisfy because it overlaps with things that are already allocated, or it will ensure that if you give it a sufficient wildcard request of a given size, it will go find a free region for you. So RMAN takes care of the part of the problem of avoiding resource conflicts. So our bus device drivers can rely on RMAN to do that. They don't have to solve that problem themselves. So I want to shift next to talk about kind of how do we name or talk about device resources for given devices. So in FreeBSD, the way we choose to name devices is by a tuple of a type and a resource ID, which commonly the variables we use all over the kernel are spelled RID, so I might call it RID. Types include things like sysres memory, which is your physical memory address space, or sysres IRQ for interrupts. We also have a couple of other ones I'm not going to mention, but another type of address space that may not be an obvious one at first to think about are PCI bus numbers. So a PCI domain has bus numbers from 0 to 255, and bridges can claim a region of those, kind of like an I/O window. And so we actually have RMANs to manage those bus numbers, and that's how we manage avoiding conflicts and all the same problems with bus numbers. And then a given bus defines what kind of scheme it's going to use for resource IDs. So some buses, like ACPI and Simple Bus, where they can just enumerate when you ask it what resources the device has, they use a pretty simple scheme of just 0 to n for however many resources you have. For example, in ACPI, when we enumerate a child, we get to call a method underscore CRS to get the current resources for a child device. And then we can walk that list, and for every memory device we see, we'll start with the first one being 0, and the next memory device being 1, and so forth. And the first interrupt, and probably only interrupt, being 0. And if there's an I/O port resource, the first one's 0, the second one's 1, and that's kind of how they're all named. In PCI, we do something a little different. In PCI, we use the offset of a bar in the PCI config space address, or PCI config space, as its kind of resource ID. So if you have the very first bar 0, we will use the address of bar 0 in PCI config space as its resource ID, which happens to be hex 10, and so forth for all the different bars you might have. In this case, this means that we don't have, in other buses like ACPI, you might have two different resources with a resource ID of 0, one a memory resource and one an I/O port resource. But in PCI, you don't have that, because in PCI, a given bar is one or the other. And so, PCI bar 0 is either going to be a memory or an I/O port resource. Or if the bar is not valid, there won't be a resource for that at all. And then for interrupts on PCI, we use 0 for the kind of legacy interrupt pin interrupt that you can have. And for message signal interrupts, we use 1 to however many you've allocated. And that's how you can tell which type of interrupt you're working with on PCI. But the important part, I guess, is the RID is something the bus defines. And so you have to know when you're writing a device driver what your bus uses. And as a bus, you have to pick a scheme for how you're going to consistently name your resources. So how do we keep track of that model of we're going to have resources named by type and RID and as a tuple, and we're going to keep track of what resources our devices have. So to help with that, we have a data structure called a resource list, which is struct resource underscore list, and it holds a linked list of entries that are of type struct resource list entry, which is somewhat obvious. And each entry holds, which we often in the source code will call the variables RLE. So each RLE holds things like the type, and the size of the given resource. It also holds its RID and kind of the valid range. In some cases, the valid range might be very constrained. If it's a firmware assigned range of exactly where the resource lives, then the start and end of the range correspond to the size. But if it's actually variable and you could move it around, then the start and end might be much broader, and the size tells you within this range, I need you to find a chunk of this size to use as the resource. The mere existence of an entry in this list does not mean that the system has gone and allocated a resource for you. Resource lists are just how we keep track of what the set of resources a device kind of can use and has available, but not necessarily that they're allocated yet. When we do want a resource, then we'll take the information in a resource list entry and use that to call a resource manager to say, give me a chunk of resource of the right type. And then when we get back the resource object for that, that becomes kind of the backing resource for this RLE, and we'll save it in the RLE. So let's talk a bit, I know I'm just throwing a fire hose of stuff at you, about a bit of kind of this life cycle or states that a device, an individual device resource can go through. So when we've added a resource, we've put it in the resource list entry, and I didn't really quite name that. But one of the things we can do is some buses don't know about the resources a device has. Like the legacy ISA bus, we rely on obscure things like hints, or there might be some other devices that kind of use other tables to find what resources they have and have to manually add them. But on many buses, like PCI or ACPI or other things, the bus itself has a way to find out what resources you have been assigned. And if that's true, then that bus needs to ensure that even if you don't have a device driver attached, that resource is still active, and we need to make sure it's reserved from the address from kind of the resource manager, so we don't hand it out to somebody else that does a wildcard request that says, I just want a random chunk of address space of size X. So buses that can identify the resources of children belonging to them while they're enumerating them, they're responsible to reserve the resource, even if the device driver is not attached yet, to ensure that nobody else can get it, because it's actually active, even though the device driver is not active. But once a device driver actually asks for the resource by calling bus alloc resource, then the resource is allocated. And that means that we've allocated something from the resource manager, and we definitely know the child has it. But in order to actually use a resource, an allocated resource needs to be activated. And normally the way that happens is when you call bus alloc resource, you can include a flag, RF active, that almost every driver does, which kind of does this all in one step. And I'll talk more about why where active can, I guess I'll do it now. So one example of why active can be separate from just having the resource allocated is active might mean, for example, you've turned on decoding for the device. So in PCI, for example, we have a command register that decides whether or not your PCI device is actually listening for requests for memory access or IO port access. And so one of the differences of an activated resource versus an allocated resource is an allocated resource may not actually have decoding turned on. It might have already been by the firmware, but it's not guaranteed. Whereas when you activate the resource, the PCI bus is going to make sure that decoding is turned on by writing the right bit to the PCI command register for your device. And then if you have an activated resource, that means it's all hooked up in the system and decoding. That's great, but you as a device driver might still actually need to use it. Like you might need to read and write a register. And for memory and IO port resources, that's yet another step. You need to map the resource to have some kind of mapping you can use. And typically that's also implied by RF active. There are some ways to turn that off and to maybe request a specific mapping, but we won't go into more of that right now. Whoa, that's not what I wanted. All right. So we talked a bit about resource lists and what we store in them. What are some of the actual functions that a bus driver uses out of this API? So first of all, bus drivers have the ability to store data about each child device. If you're familiar with device drivers in FreeBSD, you know that devices can have a soft C, their software context that a device driver uses to store information about itself associated with each device. So if I'm a device driver for a NIC and I want to have somewhere where I store my MAC address, I'm going to have a soft C that can have multiple for each instance of the device that's in the system, and I'm going to store the MAC address there. Well, instance variables, or IVARs, are kind of a similar thing, but it's not for the child device driver, it's for the parent. It's where the parent bus device gets to store information about each child device. And this data structure is the right place for a bus driver to put its resource list. So if you're going to be tracking resources, one of the things the bus driver needs to do is it needs to instantiate a struct resource list inside the IVARs for each of the children, so in each IVAR for each child. And you can use resource list init to create those, and you can use resource list free when you're deleting a child to clean up and kind of free any entries that are left hanging around. As you're enumerating resources, as a bus driver, for example, PCI, if you're walking all the bars and sizing them and figuring out how big they are, you can use resource list add to add entries to the list. And if you need to reserve them, like I mentioned PCI can do, there's resource list reserve for that. And then finally, there's a couple of helpers, resource list alloc and resource list release, that are useful in your bus driver's bus generic or bus alloc resource and bus release resource methods. So they're helpers that take care of finding the resource list entry, making sure that the device is asked for a resource that's a known one, and then asking the parent for the resource and kind of fixing up the RLE after it comes back down, and then unwinding that and release. So the last really big topic I wanted to talk about, yeah, we might make it on time, one of the things we have is we have a couple of different sets of generic helper routines for bus drivers to use so that you don't have to re-implement everything every time in a bus driver. We can share and avoid some of the copy and pasted code, at least some. And we have a couple of different groups of these. So the first one, and I'm going to talk about all three of them, is named bus generic and then the name of the method. There's a bus generic RL and then the name of the method. And then one that I added this past year is bus generic RMAN and then the name of the method. But we're going to walk through each one of these individually. So the first one is just bus generic star. And for the most part, these methods are quite simple in that they assume that I as a bus don't actually handle this request, but my parent will handle it. And so for the most part, the bus generic methods, like bus generic setup interrupt handler or something like that, they just turn around and hand the request up to the parent and say, here, you deal with this. Like, I don't actually deal with this directly, but you can deal with it. And so using this request will kind of bubble up through the device tree until they get to a level of some bus driver that does handle it. Then the request is handled and it kind of, the reply falls back down. But, this is one of my soapbox parts, there are a few cases in this API that I think are wrong. But I don't think they're actually good methods, good matches for being a placeholder method. So the first one is something called bus generic probe. And bus generic probe's job is it is actually a way to allow device drivers for a given bus device to run their own kind of special routine called an identify routine to try to discover devices that the bus device might not know about. It's kind of obscure. It's used more on pseudo buses than on physical buses. But it's a way that a driver can kind of create devices when it needs to that are attached to something else. But the key thing about bus generic probe is that that has nothing at all to do with a device probe routine. A device probe routine's job is to decide if a candidate device is a device that it as a driver can handle. And if it is, it's supposed to set the description of the device and return a value saying kind of how well it can handle it, like what its preference. Is it a very specific probe device or not? And bus generic probe doesn't do any of that at all. So it's horribly named. And nothing should use it as a device method for device probe. And I think it should be named bus identified children, meaning go walk all your device drivers and try to identify any children using the device driver to do that. In fact, one of the things I've been doing this week is that the next few slides, I've been hacking on all this, and I've got a queue of about 40 patches now because I found a bunch of other device driver bugs doing it. The next one that I think is poorly named is called bus generic attach. So bus generic attach is what it does currently is it assumes that your device bus, your bus device already has children devices, and then it will try to probe and attach all the children devices you already have. The only problem is, where did the children devices come from? They have to come from somewhere. And what's supposed to happen is your bus should have an attach routine that first goes and figures out what kind of child devices you have. Maybe it calls bus identified children to let device drivers find it, or maybe it does a scan of your PCI bus. It needs to do something to add the devices. Then it can call this routine to actually go attach drivers to the devices. But standalone, it's not good enough. If you just make this your attach routine, it's going to do nothing because there's no child devices to attach. Like, you have to create them and attach them. So similarly, I think it's not actually good as it's named and should be renamed to bus attached children to just indicate the part of kind of the logical step it's doing. And then lastly, we have bus generic detach. And this one is a little more, this one's almost to what it should be. But in particular, in general, detach routines for a device driver are supposed to unwind all the state that is done in an attach routine for the device driver. So if you've allocated resources, you're supposed to free the resources. If you've set up an interrupt handler, you're supposed to tear down the interrupt handler. So if you've added children devices as part of your attach routine, you should not only detach, but you should delete the children devices as part of your detach routine. And today, all bus generic detach does is it goes and detaches drivers from all your children devices, but it leaves them hanging around. So you have all these kind of orphan children devices left around. So, to my view, it's not sufficient to be a detach routine standalone as it is, because you need to do both things. You need to detach drivers and you need to delete the children. So I think it should be renamed to just bus detach children. And we already have an existing function called device delete children, which I argue should maybe have a bus prefix after doing all this. And its job, it will actually do the deleting of everything. So what I've actually gotten to is in my tree now, bus detach children actually does both steps. So first it goes through and detaches everything, and if that all works and none of the child devices rejected the attempt to attach, then it goes through and deletes everything, so everything is fully cleaned up by the time it returns. So that's the end of my soapbox segment about bus generic. So the next set are something called bus generic RL. And this set of routines, it's not near as many as kind of bus generic star. It's a subset of bus routines that work with resource lists. They assume that your bus driver chooses to use a resource list to name all the devices for your children devices. And in that case, it gives you a couple of helper routines that you can just use in your dev methods without having to implement all the logic yourself. In particular, if you allow child drivers to add their own resources using bus set resource and bus delete resource and to query them with bus get resource, you can use generic versions of these and it'll handle all that logic. It also provides methods for dealing with bus alloc resource and bus release resource. And in particular, these call, under the hood, they call resource list alloc and resource list release for you. And that's all great as long as you're just naming resources and allowing your parent device to kind of handle the allocation of them. And that's true for things like the PCI bus driver, for the most part. The one caveat of using these helpers is your bus must implement a new method called bus get resource list. And the job of that method is, given a child device, what is you're supposed to return a pointer to the resource list for it. So typically what you do in that method is you get the IVARs for your child device, and you return the resource list that you stored in the IVARs, because that's what you're supposed to do if you're using resource list. So the last set of generic bus methods, how am I on time? Well, I'm not terrible, are called bus generic RMAN. And these are ones that I wrote this year. Well, I wrote them several years ago, but I finally got them merged to the tree this year, is a more accurate way of saying it, that tries to reduce a bunch of code duplication we had, in particular in many of our Nexus drivers, but also in a couple other places. And the idea of these helper methods is you're not just tracking resources for children that you're naming in a resource list, but you actually have a resource manager. You're responsible for some kind of address space, and you're responsible for actually sub-allocating things out of that address space to satisfy requests. So for example, the Nexus devices that sit at the top of our tree, they're responsible for the global address spaces we have, like the set of all the interrupt lines, or the set of the entire CPU physical memory address space. So they need to work with an RMAN to sub-allocate and figure out a suitable resource allocation for some child device that wants a resource and then hand it back down. And so these are a set of helper routines for several bus methods that will do kind of all that for you. The one caveat is you need to implement a new device method called busGetRMAN that, given a resource type and flags, will return what RMAN is suitable for that your bus device has for that given type of resource. It also has a couple of other helpers that it'll handle bus activate and deactivate resource for activating and deactivating resources. The only trick here is a couple of years ago I added new methods called bus map resource and bus unmap to solve a couple of problems. One of them was kind of actually this problem, is I wanted to be able to have only the logic that's actually specific to, say, x86 or ARM64, which is how you map a resource. I wanted to have a hook that's just that. And also so you can map only a subset of a resource and not the whole thing, because there are cases when you'll see where you need to do that. So you have to implement those two methods. And if you do that, you can use all these kind of generic helpers, and it took out a lot of duplicated code among many of our Nexus drivers. So That's kind of the overview I wanted to give of some of the APIs we use. And for whatever remaining time we have 5 minutes, we'll see how this goes. I wanted to walk through a couple of bus drivers we have in the tree and how we kind of put these bits together to implement these drivers. So the first one I want to talk about is the driver for PCI bus themselves. Or the PCI bus. Note that this is the buses that have a bridge at the top, either a host to PCI bridge or a PCI to PCI bridge, and then various PCI devices into the bottom, which can be more PCI to PCI bridges, or they can be a NIC or a USB controller or something like that. But the logical bus that has a bridge at the top and things at the bottom. So PCI-X devices represent those. PCI buses don't inherently have any kind of address spaces that they're responsible for. That all comes from the parent bridge. It's the parent bridge's job to actually deal with finding me a resource when I need it. But they are responsible for keeping track of what resources a given PCI device has. So they do use resource lists. And there is a caveat about resource managers. There's this weird thing that VFs have to do for SRIOV that I'm just going to ignore for this talk. But for the most part, ignoring VFs, they don't have to deal with resource managers. They're just dealing with keeping track of what resources I have from my bars. So as we enumerate devices, we size all the bars, and we use resource list add to add every bar to the resource list for my given device. If the device has actually been assigned a valid range by the firmware during boot, then we'll also reserve that resource range to ensure it's reserved. And then that means that for the most part, we can just use bus generic resource or RL and resource list star to handle a lot of the resource management. And we don't have to deal with too much of the gross details in the PCI bus itself. And then, as I mentioned earlier, the PCI bus does have custom methods for activate and deactivate to deal with the bits in the PCI command register so that we turn them on when you're activating a resource. So the next one I wanted to talk about is the PCI to PCI bridge driver, which I have a bit of a love-hate relationship with. So we mentioned earlier, in the earlier part of the talk, about the fact that bridges need to have I/O windows, and they need to reserve space for the I/O windows from the parent, and then suballocate that to children. So in our current driver in the tree, we actually create new resource managers for each I/O window. And we allocate a resource from the parent bus for my entire window, and then we add whatever that resource that we got from the parent, we add that as regions to the resource manager for the corresponding resource manager, and then we suballocate out from that to hand out resources to our children. And the resource that we get from our parent, we don't actually need to work with it and do individual register reads and writes. So we mark it as active, but we say we don't need a mapping because we only need to create arbitrary mappings we're not going to bother using. However, the one tricky part of this is when a child device wants to allocate a resource. It gets some resource from my RMAN, and that's a smaller resource than my window. It's some subset. And I now want to give a valid mapping to my child device driver so it can do memory mapped I/O. It can read and write the registers. Well, how should I do that? What we used to do when I first added resource managers to the PCI driver was a gross layering violation, where I would take that resource that had been allocated down below, and I would pass it all the way up to the root of the tree to construct a mapping. And that worked. If you ignore things like translating bridges, it worked. But it's kind of gross. Really, bus driver, you should only have to be responsible for and dealing with the resources that you've handed out to somebody. If you didn't, if you're a bus driver and you get a request for a resource, you should handle it. It shouldn't be your job that you ask somebody else to handle something you created and handed out. And so the way I resolve that is I have this parent resource that I've got from the top side. And when I want to map some small part of it, then I explicitly in this driver ask for a mapping of just that small part of it. And I get the mapping back up from my parent, and I turn around and install that mapping in the resource that I hand to my child, and then it gets a valid mapping for just the part that it cares about. But I've allowed the parent to figure out how it wants to do the mapping. And if it needs to do translation or whatever, I allow that request tailored to kind of go up the tree. So what does that look like? So let's go back to a little bit of our hardware example from before. So we have physical memory. When the PCI to PCI bridge driver attaches, where am I at? 1 minute? All right, I'll try to finish this. When the PCI to PCI bridge driver attaches, it gets its window resource kind of for the whole I/O window out of RAM. and it creates a resource manager. That's the whole thing. Then when my NIC driver attaches, it's going to ask for its first bar. So we go to the resource manager and say, hey, can you give me the resource for bar 0? And it does that. The next step is we need to get the mapping. So for the mapping, oh, I went backwards. For the mapping, we go find just a little subset of this giant resource we got from our parent, and we say, give me a mapping for that. Then we copy that into the bar resource and hand it back to the NIC. And now it has a fully constructed valid resource with a mapping for the thing that it allocated. And so we'll keep doing that for another bar in the NIC or maybe a USB controller. And that's kind of the final state that we ended up with and how we get valid mappings. All right, I think I'm done on time, so I can't do my last 2 examples, but you can come ask me at the end. So that's it. I have 2 more on my slides. But.
Thank you, John.
Sure.
I think we can entertain 1 or 2 questions if anybody has any.
Yeah, here. Okay, and you should read that and you can ask questions, because these are useful tools.
Looks like no questions from the audience. In that case, please give John a good hand. Thank you, John.
Okay. Yeah, I'll attach them, or however we can upload them and they'll go in.
Okay. I'd like to introduce Alan Jude to you for the last talk before the closing session. And I say I'm getting hungry already. But I'm not hungry for building an application of an appliance, what this company is doing.
Yeah.
So
okay.
give him
So.
hand.
Yeah, so today we're going to talk about how to build an appliance using FreeBSD and how to make use of the various building blocks that FreeBSD provides that allow you to build an appliance more quickly and easily than you can out of other competing operating systems. So my name is Alan Jude. I'm the FreeBSD engineering manager at Clara, which is a FreeBSD services company, and I'm both a FreeBSD and OpenZFS developer. So quickly walking through what we'll go over today, starting with the introductions that we just did, and then looking at, the first step of having an image to build an appliance with is how do you actually get that image on the appliance, and how do you then manage updating it, and so on. But also looking at how you secure it so that only the software you built specifically for that appliance will run on that appliance and not other software that wasn't meant to be there, to make sure that the images you built are what's running and not something malicious. And then once you have appliances in the field, you have to maintain them. But not every appliance is allowed to use the internet. So how do you deal with that? And then we get to some of the more interesting things that FreeBSD can do, like defining your own custom security policies that are different than the defaults in FreeBSD, and how you can do that in an extensible and maintainable way. And then looking at package management, right? There's usually more than just FreeBSD that needs to go into an appliance to make it useful. And so how are you managing the third-party software, but also how do you bundle your own software that goes on the appliance and be able to maintain it and keep it running? Then we look at some interesting use cases from industry, such as immutable machines that won't change, like a kiosk that needs to forget everything it learned every time you reset it. Or every time, it's been idle for a couple minutes and whoever was using it is done, we want the machine back to the pristine state. Or, for important industrial controllers, we need a way to reset it back to default if something goes wrong so it'll work again. And then we can talk a bit about some best practices that we've learned from helping various vendors maintain a fork of FreeBSD for building their appliance or whatever, and some of the lessons that we maybe can all learn from that to make that task easier and make, updating less of a pain and less expensive. So in general, FreeBSD provides all of the building blocks you might need. We've often say it's like a Lego kit, but some assembly is required. All those pieces don't, make an appliance by default, but with a little bit, with the little Lego instruction book on how to put all that pile of pieces together, you can make something very polished out of it. So just a quick introduction to myself and Clara. We provide basically professional services around FreeBSD and OpenZFS. So that is developing features. Recently, we landed a bunch of things into upstream FreeBSD and in ZFS, as well as support and maintenance. So if you have a fleet of FreeBSD machines or you're building an appliance and you need support from experts on FreeBSD and ZFS to maintain those, and we do that. And we also help interface with the community and provide advocacy so that as you upstream things, we can increase adoption of that and make sure that those features have a long-term viability within the open source community. But starting with our first topic, which is how do we actually generate the initial image and make an appliance out of FreeBSD, and how to make $YourBSD easy and reliable and maintainable. So the first step is using Poudre, which is originally the FreeBSD package building tool, but owing to its cross-compiling capabilities, eventually got turned into also the easiest way to build an image for whether it's a Raspberry Pi, or making VM images, or making cloud images for Amazon and Google and Azure, and so on. And So this allows you to kind of take the existing bits of FreeBSD and turn it into something you can use. So in order to build the packages, you need to have a ports tree checked out as part of Poodrare, and you create a jail, basically the target system you're building these packages for. With Poodrare image, you can reuse that jail that you already built, or in one of the main advantages of Poodrare is you don't have to build that. You can download the official FreeBSD images and create the jail from the tarballs instead. So you can have a zero compile custom FreeBSD by taking what comes with FreeBSD, and then with Poodrare, making an exclude list of I don't need these files, and then an overlay of here's all the files I want to put on top after we're done, and then a list of packages that I want, and get a custom image that is FreeBSD minus what you don't need plus what you do, and now you have a one-line script that will reproducibly create an image of whatever version of FreeBSD without the bits you don't need with what you do, and it's good to go. If you do have your own fork of FreeBSD, where you've changed the code, or a big source.conf that disabled all the features you don't need, you can have it compile that or reuse an existing obster to install the jail. But it lets you take whatever customizations you have and turn it into a usable image in a reproducible way. Having an overlay directory of what you want to put on top, whether it's a couple of configuration files or whole binaries or a web application or whatever, overlay all that on top, but that can come from your own Git repo or whatever you need to make it manageable and sustainable and repeatable. We then extended that overlay feature with the pre and post scripts. So the pre-scripts allow you to change how the disk is laid out. So if you want to apply custom partitioning, or you want to put specific ZFS data sets, we need a separate data set for where the database is going to go, and we need a different one for the mail spool, or whatever your application is going to use it for, you can customize the list of ZFS data sets and get it exactly how you want. And then the postscripts allow you to touch up and do things before you go to image generation, or even after image generation. So that can be the step of, all right, I've made a raw disk image. Now I need to turn that into an Amazon AMI so I can upload it to the Amazon Marketplace. And then a second postscript that then says the same thing and uploads it to the Microsoft Cloud Store, or whatever combination of places you need to do that. Right? I'm going to make a QCOW image for people that use KVM and a VMDK for people who use VMware, or whatever the different things you could do. And so the key to successfully making one of these images is to avoid ever having to manually edit the image, right? You want to have this process with the overlay control what goes in the image and make the image perfect every time, and in a way where you can go back and create the image exactly the same way later, or you can create exactly the same image based on a newer version of FreeBSD without having to manually go in and remember to remove the SSH keys, host keys that got generated when you booted it once, right? You don't want that. You want to have everything done the same way cleanly from the beginning. And one of the other great things that Poodrare image can do now is the output, in addition to the raw disk images or VM images, can be a ZFS replication stream. And we'll talk more about that when we get to upgrading the OS, of how to use that to pristinely make new boot environments so that you have a fail-safe way to upgrade. So the steps for building an image are, you can start with stock FreeBSD, which, as I said, you don't even have to compile. You can download it from FTP if you want. Or if you have a customized version, you can compile it your own whatever way. But you can start by inheriting reproducible builds from upstream, or pristine images from upstream, so that the checksums of all those files are going to match what was in normal FreeBSD, if you have compliance requirements that do that. Then you add whatever features or files that you need, whether that's your own software, your configuration files, your settings, your custom data sets, whatever it might be. You just sprinkle in your magic, and now it's not just FreeBSD, it's your BSD. Then you take the list of software that you need, right? If you're going to have a web interface, maybe you need to install a bunch of Python or Node or PHP or whatever, so that you'll have that working. And once you have all that, then you can post-process it and turn it into, all right, here's a USB stick image that will install our appliance on your hardware, or here's a disk image that you can just DD onto it, or here's the thing to run it in VMware or Azure or Amazon or whatever you need. And you get all those images, and after those steps, you now have an appliance that you can take to market and start selling. So looking at a real-world example of this, one of our customers makes an email server messaging software. And in the past, the way they did this is they built their own package of it and their own repo hosted on their website, and would tell people, okay, install FreeBSD, and then change this config file to point to our repo, and then run package install our software, and then go and configure it all, and then now you'll have our software running on your FreeBSD machine, and it'll be great. And that works well for people that are already using FreeBSD, but the customers are like, well, we want to just one-click deploy this in the cloud, and we don't really know that much about FreeBSD, but we know that it's what we want to use. And in particular, the reason they wanted FreeBSD for this email appliance is because ZFS would store the email much more efficiently with transparent compression and scales to lots of files and directories a lot better than other file systems. So they wanted FreeBSD, but somebody who hasn't really heard of FreeBSD or ZFS probably doesn't know how to tune ZFS to deal with lots of small mail spool files. So instead, all they could do was use Poudre image and install FreeBSD with their custom package on it and all the configuration and an already laid out ZFS with all the right settings, and output it as an AMI and click a button and put it in the Amazon store and be able to charge people per hour to run their application based on FreeBSD. And so, if you build it, you can start having an appliance in the same day. As long as you already have your software or whatever unique selling feature that is your appliance, you can base that on top of FreeBSD and have a product in almost no time. But then, how do you make sure that it's running the right code? So Secure Boot isn't the solution to everything. It's had many of its own issues, but if you manage the keys properly, it does actually do what it says on the tin. The main issues, especially the ones we saw recently, were caused by the supply chain for how EFI works. Companies like AMI make the reference firmware, but then that's not what you run on your motherboard. You get the firmware that's been adulterated by your motherboard manufacturer. And in order to make sure that that's correct, AMI includes a bunch of test keys in their source code repository that they give to your motherboard vendor. And those keys, in very big capital letters, say, test only, don't ship this, and don't trust this. But apparently they used the wrong build flag and bundled all those keys as trusted keys in your BIOS. And because that source code with those keys ended up on GitHub, anybody can sign a binary that will probably be trusted by your motherboard unless you've patched the firmware. Whoops. But if your firmware only trusts the keys it's supposed to, including your new key that you've done, then you can take these images you're building with Poudre and include a signed loader that will only load the right software. And the shortcoming right now with FreeBSD is the signing covers loader.efi, right? So your motherboard firmware will see loader.efi, verify that the signature is in its trust database, say, yes, that file has not been adulterated, and run it. But loader.efi doesn't cover very much of the FreeBSD footprint. But you can extend that by basically embedding your kernel and even as far as your whole /boot file system as a memdisk into your loader.efi, so that when it's signed, now your loader is signed, but also the kernel and all your boot configuration is now coming signed. Similar to the concept of the universal kernel image thing that Linux is doing to solve exactly the same problem. And also, you can enable the very exact feature in the loader. So now it will only load things that it thinks are signed by the next step. So your loader.efi is baked into it, has a trusted key, and uses that to verify a manifest that has hashes of the files, and it will only read a loader.conf that is verified, or all the loadable kernel modules you might have. It'll only load ones that are actually verifiable. And then if you also have veryexec enabled once the kernel starts, you can carry that all the way through to every binary that you try to run on the system now has to be signed, or we're not going to let it run. And so now we have assurance that our kernel is a legitimate one and not been modified, and that our loader is only going to load files that have valid signatures. And we can carry that root of trust we started with of just loader.efi all the way through to the entire appliance. This also lets us lock things down more and play some interesting games. For one customer, we made a version of the loader that would refuse to load any ZFS dataset that didn't have the right GUID. And so this loader would say, that's the right boot environment, and I refuse to boot anything else. And this way, they would only be able to boot the right operating system or the rescue system and nothing else. And this way, again, even if you had access to write to the file system, you couldn't get this system to run not the right software. And so it would stop unauthorized boot environments or just running the wrong version from happening. Again, this was matched up with what I was talking about earlier with the kiosk type system where every time this machine reboots, it forgets everything it knew and runs back to a pristine state. And so making sure it couldn't get out of that pristine state was important. And another thing that they used with this was they didn't run a regular version of ZFS. They ran one with a small patch where data sets could be marked as immutable, which is kind of like read-only in ZFS normally, except for you can't ever turn it back off once you've set it. And so this data set is now set in stone, and you can never modify it again. Of course, it's only enforced by this specific ZFS module, not a normal one. And so making sure the system wouldn't boot anything except for ones that would enforce these same rules was important for that actually to work the way it was intended to. And then another interesting thing we did using ZFS was locking down the encryption keys. So when we're going to sign these EFI firmware images, we need the private keys to do that. But when we're not in the process of signing a new thing, we'd really like it if those keys weren't just laying around on a hard drive somewhere. So putting the keys in their own ZFS dataset on the build machine with ZFS encryption enabled, and then you unload the key when you're not using it. And so now the data is actually at rest, right? The biggest problem with disk encryption is that when the drive is mounted, usually the encryption key is in memory and all the files are accessible. But with ZFS, you can have different encryption keys for different data sets, and you can unload the ones you don't need. So, if we're you're shipping a new release to customers once a month, for the other 29 days of the month, that key is at rest, and unless you have the right passphrase to mount it, that key is not reachable. And this way, if a system gets compromised or something, there's less chance they can get away with your private key. And it makes sure that we're actually taking full advantage of disk encryption that way. Back to veryexec. As we said, it can prevent the execution of untrusted binaries. So if someone does manage to smuggle some code in or something, they won't necessarily be able to run it. What's really interesting is that you can extend this concept to scripting languages even. So you sign the Python binary, and so the Python binary is not fine. But if it's going to run any .py file you feed it, that's not really helping you very much. But you can basically modify the Python binary so that when it's opening Python scripts, it opens them with the O-verify flag. And the open from FreeBSD will fail if the file doesn't match the expected checksum fed in the veryexec manifest. So if you try to load some unknown Python file or some modified Python file, Python will fail to open it. So now even the Python code you're running is the right Python code. Veryexec could still be more integrated into FreeBSD. It's not as widely used as it could be, and so there's some shortcomings still, especially it was designed in an era when you'd have one UFS file system, not 17 ZFS file systems. But we're working with the original vendor to get more of those changes upstream and get the performance improvements that will make VariExec more applicable to high-performance systems, not just smaller embedded appliances where there's not going to be that many binaries and they're not going to be changing. But even now, it does provide a lot of protection and quite a bit of flexibility. It just, as with anything, could be better, and we continue to work in that direction. So moving on to upgrading. If you have a whole fleet of these appliances out there that you're responsible for, you have to try to keep them up to date, even though you don't always get to decide how that works. So I say, when appliances are deployed out in the world, they're deployed in all kinds of different environments, often not ones you have any control over. And so that means your upgrade mechanism has to be able to cope with all the different versions of things that could be out there. So you never know what the network's going to look like, or if there's going to be a network, or what. For some banking systems, the computers are air-gapped, and you're only allowed to enter that vault with read-only media. So you need some way to bring the update in there with you and apply it and not be able to take anything back out with you. And while that's helpful, that's something you can build, then you get other things where this appliance is going to run in a place where it's really inconvenient to send somebody to go do the maintenance, right? The bank is usually relatively accessible, even if it requires an appointment and special media and so on. But when this thing is controlling the battery chargers at the bottom of a mine, maybe it's harder to find somebody who wants to go down there and work on it. And so you have to be able to adapt to these types of environments. And the biggest thing is you need to be sure that it can't go wrong, right? If you try to upgrade the system and it doesn't work, you need to be able to get back to a working state immediately, not after a bunch of debugging, right? You need to get it working again, and we'll debug it offline without production being down the whole time. And so this is where ZFS can really help. Similar to the concept of NanoBSD, using boot environments, you can have your new image and use the boot once feature to say, all right, we've deployed the new image that we created with PuDRA image of the next version of our appliance, N+1. And we've now brought it to the bank on a CD, or somehow got it to the bottom of the mine, or posted it on the internet and people are going to download it. And we'll apply that new data set, and we say, okay, reboot, and it'll start the new version. And so when boot once happens, we put a little note at the beginning of the ZFS pool that says, instead of the default boot environment, next time, and that time only, boot this new environment. And when the bootloader sees that, it will do that, but erase that message so that if you power cycle, it will go back to the default. So one time, we'll boot the new image. And if that works, we have a little script running in there that will say, okay, I managed to stay up for at least 15 minutes, probably okay, I'm now the default. Or it can do its own diagnostic or whatever criteria you want to be sure that this image, the new image actually works. It has served enough traffic that we might make it the default now. If it doesn't, somebody just power cycles the machine and it boots the old boot environment that was working fine, and production is back. So you have a way to try to do the upgrade, but if it goes wrong, you don't have to mess with it, you don't poke at it, you just go back to a working image and then debug the logs after. That way, production doesn't stay down while you're trying to figure out why this upgrade went sideways. But you also have to look at how do we manage upgrading those offline or air-gapped systems. So we had, for a different customer, build a script that could upgrade whatever machine we happen to plug it into, which were appliances based on FreeBSD 8 or 9 or 10 or 11, and upgrade them to FreeBSD 13. Well, if anybody remembers, back on FreeBSD 8, your root disk was called ADAS4, and now it's AD4, or the other way around, sorry. But the SATA disks were numbered differently based on the port number instead of the device number, and with a different device name. So for some of them, we have to rewrite the FS tab. And then some of them were MBR, and some were GPT. And the partition numbers were different. So the upgrade script had to find the right partition that actually contained the working system, and then be able to upgrade it, and deal with any changes that are going to happen between the versions. But one script had to do all of them, and you don't know what you're getting into when you're going in, and you have no internet while you're doing it. So it takes quite a bit to do that. Oh, and then we had to upgrade Postgres. And being that some of these were back to FreeBSD 8, that's a version of Postgres where you have to dump the whole database, and then upgrade Postgres, and then import the whole database. But that means we need the old version of Postgres to work on the new FreeBSD temporarily while we do that. And it needs to check that there's actually going to be enough disk space to dump the whole database and then read it back. So it was not that easy. But once built, and again, using that fail-safe mechanism, we were able to do all that and not have any risk that the database wasn't going to work after, because we'd always be able to go back to a working version. And then the other problem you have is that the appliances are part of the customer's infrastructure, right? You don't own the appliance anymore once you sell it to them. And so you don't get to decide when they want to update or how often they want to update. And that's how you end up with FreeBSD 8 machines that are still waiting to upgrade when you're shipping FreeBSD 13. And you don't get to pick when the maintenance windows are or what the network looks like. And so there's that many more complications. But with ZFS and Poudre, we mostly have all of that under control. And if we design the appliance from the beginning knowing that these are the challenges we're going to face, then there are solved problems instead of new wrinkles. And that led to the next idea, which is if we're using ZFS replication to ship the new boot environment, can the appliance actually verify the provenance of the incoming ZFS stream before it tries to process it? So a couple of years ago, Joyent, for their public cloud, came up with a concept like this because they only wanted to allow ZFS receive of images sent from elsewhere in their cloud, not from just anywhere. Because if you made a malicious ZFS replication stream, you probably could find a way to crash the kernel. And in the cloud, they really didn't want that happening. But if we're going to use all the secure boot stuff and make sure we have signatures and so on, maybe we want something to make sure that incoming ZFS stream is signed as well. And importantly, we probably want to be able to stream it through rather than have to write it to disk, verify the signature, and then feed it into ZFS. Because again, we don't want to need double the disk space every time we're trying to install a boot environment, because appliances tend to have a lot less slack space available. So the next topic is custom security policies. So when you want to do something slightly different than what FreeBSD does by default. Luckily, every security check that's in FreeBSD has hooks around it for kind of before and after. And there are these loadable MAC modules, or mandatory access control, that let you customize criteria by hooking onto those hooks and changing the answer. So one of the great ones that's included by default in FreeBSD now is MAC_NTPD, which allows one specific user, as configured by a sysctl, to change the clock without needing to be root. So after some of the CVEs in NTPD, this was done so NTPD can run as a completely unprivileged user, but that one user is allowed to change your clock. And so this is a great example of how you can make a MAC module to have some privileged process not need privileges anymore. One that I developed was for an API that allowed people to upload videos. And all that happens as the web server user. But those videos belong to other users. And so to make sure quotas and the usage tracking works correctly, I needed the web server user to be able to chown those files over to the real user that had uploaded them. But I don't want my system to allow anybody to chown files away from themselves and so on. So using a Mac module, we could implement rules that say, well, if the file's not owned by root and you're this special user, then unlike normal, you're allowed to own it over to somebody else. And by default, that's disallowed in FreeBSD, mostly because it would let you cheat at quotas. And you can picture cheeky university students owning their files off to somebody else so it doesn't count against their quota. But another Mac module that we did was for a customer that was hosting Node.js apps for all their web hosting clients. And if you know anything about Node, you know that every application assumes it's got its own whole VM. So they all would just want to listen on star port 5000. But if you're in a shared web hosting environment, every customer trying to run on port 5000 isn't going to work. But you also are not going to train every one of your customers on how to select a different port and make that work. So we wrote a Mac module that, from some sysutils, had configuration of a base IP address in the internal range. And it would basically start with that IP address and add the user ID of the user trying to listen on port 5000 to it, and generate a unique IP address for each user, and then rewrite their listen request to be on port 5000 on only that IP. And then a shell script would generate an Nginx config file that mapped the real stuff to each customer on their port 5000 and allowed them to solve that problem with this much C code instead of trying to train every customer how to change the port in their various different Node apps. But it really lets you, any permission check that happens in FreeBSD, you can add your own criteria to make it more locked down or less locked down or whatever in order to control how it works. So some examples, we mentioned the Mac NTPD, which allows you to have one user do something that normally only root would be allowed to do. There's another one, port Mac ACL, or sorry, Mac port ACL. Normally, only root's allowed to bind to ports less than 1024, right? And that's why your web server and your DNS server and all these other things often have to run as root just to be able to bind to that port. Well, Mac port ACL lets you make a list of port to user ID tuples as a sysutl and say, okay, now the user bind is allowed to bind to port 53 even though they're not root. And suddenly your DNS server doesn't have root privileges anymore. While it usually tries to drop those or whatever, not needing them at all is even better. And so recently we also upstreamed some work on NetSNMPD so that it can now run using sysutls and not need to open dev kmem. So that allows it to now run completely unprivileged. So with the port ACL stuff, you can listen on, I think it's 60 something, whatever port SNMP uses, and get access to all the stats without needing any root privileges and without losing any stats. So the port in FreeBSD had the option called jail for running SNMPD in a jail, and it would make it just not open dev kmem. But if you did that, you lost like 2 or 3 MIBs full of stats. And now you get all of the stats without any permissions. And another really interesting one is poorly named called BSD Extended. And this Mac module actually implements a file system firewall. So you get firewall type rules for your file system, where you can say, this user is not allowed to read files that match this path. And really specific things you can get down to giving you a lot more control than the standard Unix permission model or even ACLs give you to allow and deny specific read and write requests or open or changing of permissions or whatever. And so it really shows that the Mac module gets beyond just the simple permission checks to be able to implement all kinds of really expansive changes to the system. So it gives you a large degree of flexibility. There are a whole host of ones already built into FreeBSD, but building your own is quite simple. Like the example for the file API one, it was, again, one screen full of code to be able to control something that would be impossible otherwise, or other versions of it would have involved sudo and things like that you don't want. And in fact, actually, Baptiste recently wrote MacDo, which basically allows you to use this Mac framework to allow certain users to run commands as a different user, but built into the base system and without having to use setuid. Right? You're just saying, you know, if you're this user ID, you're allowed to run that command as that user ID, and we don't have to have any involvement of the root user or using setuid. So next, we have the package management, right? Your third-party software, all the other stuff you want to include in your appliance. So the port system provides this huge selection of apps, and it provides this framework that simplifies packaging software. But that also means it simplifies packaging your software. So whether, you know, it's the web interface that's going in your appliance, or extra tools that you need to install, or whatever packages you need, if you use the ports framework via its own overlay system, or just your own category, or whatever, there's plenty of ways to add your own ports to the ports tree. Then you can use the same mechanism as used for the other software to get everything into the system. Also gives you the options to control how often and which software gets updated, right? When you're building your own appliance and shipping your own package repos for it, you can decide if you want to use the quarterly package set, which is, you know, updated quarterly, but mostly only gets security updates and isn't going to have big feature changes happening unexpectedly, or the latest repo, knowing that you're going to get improvements faster. But you also get to decide when to pull things in, or we're going to pull in these updates and not those, and or, you know, this change broke something for us, so we're going to revert this set of ports to an older version. It gives you the ability to decide exactly what's going to ship to your customers. And with some other work that we did recently, it is now possible to do the equivalent of package audit, which you can run on one machine to see if it has any vulnerable packages installed. You can now do from Poudre on a repo. So you can say, this entire repo I just built for my appliance, are there any known vulnerable packages in it? And then you're going to find those and be like, okay, I'm going to, you know, update this port early to get the fix for OpenSSL or whatever. And then Poudre is going to be able to take those images or packages you just built and bake them into your image so they're already installed. If you lay out your ZFS right, you can include the packages in the boot environment so that you never run package upgrade on the appliance. You go from this set of working software to the next set of working software. If you've ever, you know, tried to do package upgrade across the Python version change, you know the finickiness you can run into. And on an appliance, you don't want that. And so you just go from A to B atomically. So the factory reset, again, ZFS plays a big part in this one. So obviously, using ZFS in boot environments, you can always roll back to an older boot environment and have the system back how it was. Again, depending how you lay out your ZFS, you can make sure the configuration is separated so that, you know, if you roll back to an older version of the OS, it doesn't undo any settings changes. Or you might want it to do that, right? If there are new settings that only apply to the newer version, you want to tightly couple the configuration to the version. But you have the option to do it either way, whichever one works best for you. And you can also, you know, have basically factory reset to a known good OS image. Kind of, you know, most embedded stuff have, you know, an A and a B firmware, but with ZFS you get N firmwares, as many as you want, or as many as you have room for. But you can also build a mechanism to automatically boot a rescue environment. So basically a mechanism to resolve a CrowdStrike-like situation where the system panics on boot because of an update or something. So this is inspired by work at Delphix, but using similar to the boot once mechanism that we talked about in ZFS, you can instead have a counter and say, okay, we've tried to boot 3 times or 5 times, and we've never stayed up for the 10 minutes to reset the counter to 0. So if we've tried to boot 3 times and we've not succeeded, instead of that boot environment that we've tried 3 times and not been successful with, we're going to boot the rescue environment that either allows the customer to try to figure out what's going on or phones home and allows us to do a reverse tunnel into it to actually figure out what's wrong with the appliance. This can be really helpful in certain clouds that don't give you console access to the VM. So it won't boot now, but I need a way to get in and have it call you and be able to get in there and figure out why it didn't boot. Mount that other boot environment, look at the logs, and figure out where it was dying during the boot process. Or the kiosk mechanism, right, where every time we boot, we're going to roll back to a known good point in time. So this one's interesting where we actually changed the bootloader to be able to boot from a ZFS snapshot rather than the data set. So the boot environment, or sorry, the bootloader in FreeBSD can only works read-only. So it can't roll back a data set to a snapshot for you. And so we put that in the early boot stuff. If you saw Mathieu's talk earlier, right before we actually run the RC, there's some stuff to be able to run RC in a chroot, and there's a little setup script that you can run there. And we use that mechanism to actually roll back the data set to the snapshot. But before that, if we were using the data set, if you had modified the kernel, we would have booted the bad kernel and then rolled back the system to pristine and run the good user land, but we'd still have the bad kernel. So teaching the bootloader to be able to read from a boot environment or from a snapshot meant that we ensure we always get the known good kernel. And then only as we're transitioning from read-only to read-write for the root file system, then we can roll back and everything is okay. And so that allows us to basically reroute onto the correct file system. And that way we know only the right kernel ever gets loaded. And this way, no matter what you do to the file system, when you reboot, you're going to be back to the known good thing. And again, you could use the customized ZFS module if you wanted to make that even more immutable. Of course, you do have to coordinate that with the safe update mechanism so that you reboot into the new correct snapshot, not the old correct snapshot. Otherwise, you're also going to undo your update every time you reboot. But again, knowing that ahead of time, you can design it to work that way. And last thing I promised was talking some of the best practices for maintaining your own fork. The biggest one is selecting the right branch, right? If you're deciding you're building an appliance today, but your plan is to ship it, in 6 months or 2 years or whatever, if you start with a stable branch right now, that's going to be EOL by the time you're trying to ship, not the right choice. So looking at when you want to ship, you want to select the branch that's going to be the well-supported one at that time. But no matter what branch you select, you also, off to the side, using the same Poudre system, want to be building and testing your appliance with current so that every time something on current breaks, you can report it and get it fixed. Developers work on things, and if you tell them it broke your stuff 6 months after, they've moved on to something else and they don't have all that context. Maybe they're willing to fix it, but it's going to take them a lot longer. Whereas if you can be constantly testing current, finding issues and reporting them while they're fresh, they will get fixed a lot more easily. Other one is upstream first. If you do customize FreeBSD in some way and you're going to upstream it, you want to design the change from the beginning to be upstreamed. So that means generalize it a little bit and not good enough for us. And if possible, committing it to FreeBSD current and then consuming it from there rather than carrying it as a local patch until it merges. And this way you know you're not going to have to rewrite it based on the upstream feedback, right? You're going to incorporate that feedback in the original version, not later. And that's oftentimes how we see things not ending up upstream when we thought they should. If you're interested in more about upstream first, see my talk from last year's vendor summit on YouTube. And the other one is, if you're going to have a fork, rebase often. Don't wait until it's been 4 years since you resynced with FreeBSD, because it will be that much harder. And there will be that much less expertise around, or even kind of related to testing on current, if you have questions about why something changed, why this API changed, why that field went away in this call, people will remember what you're talking about if you're talking about it in proximity to when it happened. If you're asking about something that happened 4 years ago, I don't remember. Whatever the commit message says. And then, leverage what exists for tools and try to avoid, not invented here. But also, if you do find that the tool you need doesn't exist, when you build it, share it. Because other people will continue to improve it and will also probably help make sure it works on current. So next time you go to update, your tool already knows how to deal with that new thing. And the more we can share the load, the more we can all benefit. All right. 20 seconds to spare.
questions?
Is the port ACL Mac module available online anywhere or documented?
It's built into FreeBSD for a couple of versions now. You just have to KLD load it.
Oh,
and then set the config. There's a man page in base that explains how to configure it and everything. Some ports depend on it now.
Is boot from Snapshot upstreamed?
Yes, boot from Snapshot was upstreamed 2 years ago.
What's it called?
You just set the boot the bootfs to blah at blah.
Okay.
Yeah, it just works. It's not a special feature. It just has to walk the tree a little different to find the snapshot.
And just more for interest sake, you said you had a system where you had a couple of different FreeBSDs, 8, 9, 10 that you needed to upgrade. Did you consider just doing incremental upgrades instead of trying to just bring everything to one BSD?
Generally avoided that because that would have meant like n reboots versus one. So mostly the way it worked is we kind of took an M tree of the system in place, compared it to an M tree of our new image, and figured out which files went away to delete and which files of the config. We had to basically maintain the configuration file and then splat the new version over top and delete any files that don't exist anymore in the new version and do all that. But yeah, we avoided incremental updates just because we didn't want to build new images of FreeBSD 9, 10, and 11.
Oh, so you didn't have one? Okay, so no, that makes sense then. Yeah, I thought if you had updates for 9, 10, and 11, it would be easier to just do it incrementally. But yeah, if you didn't have it,
this was more just take whatever they have and bring it to 13 because that's the version we support now.
Okay, yeah, makes sense.
See, if the system hangs instead of failing during the boot, what will happen? Do you have a watchdog drive?
If you have a watchdog, it'll reboot, and then on reboot, it'll do the right one. Or a user can manually just power cycle it, and it will do the right thing. That's why it erases the boot once thing as soon as it sees it, so that even if you hang early during boot, the next one will definitely fall back to the default.
And about that, the fail-safe. If I change the system to a new version, and the boot goes well, it seems everything works, okay? But things go wrong after a few days, let's say. Yep. I see that it's not working well. Can I still go back to the previous version?
Yes, we keep all the previous ones by default. There's a couple different ways to do that. One command run from the running system will set the new default or the new boot once. Also, the bootloader in FreeBSD has a menu where you can manually select some of the older ones. And you can also consider using the fail-safe mechanism where if it fails to boot 3 times, it boots the rescue system or some older known good image.
Okay, thank you.
And you can also pick your own criteria for when an image becomes the default. So it can be, it worked well for 7 days, or it can be for 7 minutes, whatever you want.
Thank you for all the blogs and articles on the Clara's website. Can I find articles of most of the methods you are showing here?
Not all of them yet, but they're coming. We launched our new website at the beginning of this month. It's much easier to find our articles now. They're actually sorted into categories and searchable. And you'll see a lot of articles coming up soon.
Looking forward to it. Thank you.
No more questions? Okay, well, thanks, Andy, Helen.
Thank you.
Thank you.